In July 2022, the James Webb Space Telescope pointed its infrared eyes toward a seemingly empty patch of sky and captured something that made astrophysicists check their calculations 3 times. A galaxy. But not just any galaxy. This cosmic island of stars appeared to exist at a time when the universe was supposedly too young, too chaotic, and too hostile for such structures to form. The light reaching us had travelled for over 13.5 billion years, showing us a snapshot of a galaxy that shouldn't exist, at least not according to our current understanding of physics. Its brightness defied expectations. Its size contradicted models. Its very presence suggested that something fundamental about the early universe or our theories about it was wrong. JADESGS Z130, as astronomers labelled it, sits at a redshift of 13.2, meaning we're seeing it as it appeared just 325 million years after the Big Bang. At that epoch, the universe was still emerging from the cosmic dark ages, a period when the first stars had barely begun to ignite. Yet here was a galaxy already mature, already churning out stars, already defying the rules we thought governed cosmic evolution. This discovery didn't just push back the boundaries of the observable universe, it threatened to rewrite the fundamental timeline of galaxy formation itself, the cosmic dark ages before galaxies. The universe wasn't always filled with light. For hundreds of millions of years after the Big Bang, space existed in what astronomers call the cosmic dark ages, a period when no stars shone, no galaxies glowed, and the cosmos consisted of nothing but cooling hydrogen gas drifting through expanding darkness. This era began roughly 380,000 years after the Big Bang, when the universe finally cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, called recombination, space was a hot, opaque plasma where photons couldn't travel freely without scattering off charged particles. Once neutral atoms formed, light could finally stream through space unimpeded, creating the cosmic microwave background radiation we detect today as a faint afterglow. But this newfound transparency didn't bring illumination. The universe entered darkness because no sources of light existed yet. The first stars had not formed, galaxies had not assembled, and the only matter present was hydrogen, helium, and trace amounts of lithium, the primordial elements forged in the Big Bang's first minutes. These atoms drifted through space at temperatures just a few thousand Kelvin, gradually cooling as the universe expanded. Gravity, however, was already at work. Tiny density fluctuations, imprinted during the Big Bang's inflationary period, began to grow. Regions slightly denser than average attracted more matter, while less dense regions emptied further. These ripples in the matter distribution were incredibly subtle variations of only 1 part in 100,000, but they provided the seeds from which all cosmic structure would eventually emerge. Dark matter played the crucial role in this process. Unlike ordinary matter, dark matter had begun clumping together even before recombination because it didn't interact with photons. By the time neutral atoms formed, dark matter had already created gravitational wells, invisible scaffolds that pulled ordinary matter inward. Hydrogen gas flowed into these wells, accumulating in the centers of dark matter halos spanning thousands of light years. As gas piled up, its density increased, and its temperature rose from gravitational compression. Computer simulations show that these early halos were chaotic and irregular, colliding and merging constantly as gravity drew them together. The universe during this epoch resembled a cosmic web forming in slow motion, filaments of matter stretching between dense nodes, while vast voids remained nearly empty. The Dark Ages persisted for roughly 100 to 200 million years, though the exact duration remains uncertain. During this time, the universe continued expanding and cooling, but no light sources broke the darkness. The cosmic microwave background radiation stretched to longer wavelengths as space expanded, fading from visible light to infrared and eventually to microwave wavelengths. Any observer during this period would have seen only darkness in every direction, broken perhaps by the faint glow of the cosmic background itself. The hydrogen gas filling space existed in a neutral state, neither ionized nor capable of emitting visible light. Only when gravity compressed this gas to extreme densities would conditions finally permit the first stars to ignite. The formation of those first stars marked the end of the Dark Ages, but the transition wasn't instantaneous. The earliest stars likely formed in small, scattered pockets, isolated events occurring in the densest dark matter halos. These population 3 stars, as astronomers call them, were fundamentally different from modern stars. Composed almost entirely of hydrogen and helium with virtually no heavier elements, they could grow far more massive than stars forming today, perhaps 100 or even 300 times the Sun's mass. Their enormous size meant they burned fiercely hot and died quickly, living only a few million years before exploding as supernovae. These explosions released the first heavy elements into space: carbon, oxygen, nitrogen, iron, and dozens of others forged in stellar cores and supernova shockwaves. They also released tremendous amounts of energy, heating and ionizing the surrounding hydrogen gas. This process, called reionization, gradually transformed the universe from neutral to ionize over hundreds of millions of years. Ultraviolet radiation from the first stars stripped electrons from hydrogen atoms, creating bubbles of ionized gas that expanded outward at nearly the speed of light. As more stars formed and more bubbles grew, they eventually merged, and by roughly 1 billion years after the Big Bang, reionization was nearly complete. The universe had transitioned from darkness to a state where light could travel freely through ionized hydrogen, though stars remained rare and galaxies had only begun to assemble. Current observations using the James Webb Space Telescope are revealing this crucial transition period in unprecedented detail, showing the first galaxies forming during the final stages of reionization far earlier and more rapidly than previous models predicted, when theory predicted galaxies could form. According to standard cosmological theory, galaxy formation required a specific sequence of events occurring over hundreds of millions of years. The prevailing Lambda-CDM model, our best understanding of cosmic evolution, painted a detailed picture of how and when the first galaxies should appear. This model combines Einstein's general relativity with observations of cosmic expansion, the cosmic microwave background, and the large-scale structure of the universe. It predicts that galaxies couldn't form instantaneously after the Big Bang, but required time for matter to clump together under gravity's patient pull. The earliest theoretical predictions suggested that the first small proto-galaxies might emerge around 200 to 400 million years after the Big Bang, while larger, more mature systems shouldn't appear until 500 million years or later. The model's timeline rests on well-established physics. Dark matter, making up roughly 85% of all matter in the universe, began collapsing into halos immediately after recombination. These halos created gravitational wells that attracted ordinary baryonic matter, primarily hydrogen and helium gas. As gas accumulated in these wells, it heated through gravitational compression. Eventually, in the densest regions, temperatures and pressures became high enough to ignite nuclear fusion, creating the first stars. This star formation process was expected to be inefficient at first. Early stars formed in isolation or small groups, not in organized galaxies. The feedback from these stars, ultraviolet radiation, and supernova explosions heated surrounding gas, making it harder for additional stars to form. This self-regulating mechanism slowed the assembly of larger structures. Computer simulations reinforced this gradual assembly picture. Programs like the Millennium Simulation and Illustris TNG, which track billions of particles representing dark matter and gas, consistently showed that galaxies built themselves hierarchically. Small structures formed first, then merged to create progressively larger ones. According to these simulations, galaxies with masses comparable to modern galaxies shouldn't appear until at least 500 to 700 million years after the Big Bang. Even then, these early systems would be irregular, chaotic, and far less organized than nearby galaxies we observe today. The models predicted that the first galaxies would be small dwarf systems containing perhaps a few million solar masses of stars, not the massive spiral and elliptical galaxies dominating today's universe. Observational evidence prior to JWST supported this timeline. The Hubble Space Telescope, despite its remarkable capabilities, could detect galaxies only back to around 400 to 500 million years after the Big Bang. Even these earliest Hubble-detected galaxies appeared faint, small, and irregular, exactly what theory predicted. The farthest galaxy confirmed before JWST, GNZ11, existed roughly 400 million years after the Big Bang and contained about 1 billion solar masses of stars. While impressive, this matched theoretical expectations reasonably well. The galaxy showed signs of active star formation, but wasn't dramatically larger or brighter than models suggested possible at that epoch. Astronomers felt confident that while details might need adjustment, the basic picture was correct. The Lambda-CDM model also made specific predictions about reionization, the process by which the first stars and galaxies ionized the neutral hydrogen filling the universe. Observations of distant quasars showed that reionization completed by roughly 1 billion years after the Big Bang. Working backward, theorists calculated that galaxies must have begun forming in significant numbers by 300 to 500 million years to produce enough ultraviolet radiation to accomplish this reionization. The timeline fit together consistently. Dark matter halos assembled first. Stars formed within them, starting around 200 million years. Small proto-galaxies emerged by 300 to 400 million years. And larger systems gradually assembled over the next several 100 million years. Each stage followed logically from the previous one, constrained by the finite speed at which gas could cool and collapse. Theory also predicted that early galaxies should appear different from modern ones in several key ways. They should be bluer because they contained only young, hot stars with no older stellar populations. They should be smaller and less massive because insufficient time had passed for extensive mergers. They should show irregular, chaotic morphologies because gravitational interactions constantly disrupt their structures. Their chemical compositions should be extremely metal-poor, containing almost no elements heavier than helium, because supernovae hadn't yet enriched the interstellar medium with heavy elements. And crucially, they should be rare, with number densities far lower than modern galaxies. The universe at 300 million years should contain perhaps 1/10 the number of galaxies present at 1 billion years, and 1/100th the number present today. This theoretical framework had been tested and refined over decades. Observations from ground-based telescopes, Hubble, the Spitzer Space Telescope, and radio observatories all contributed data that aligned with predictions. When slight discrepancies appeared, theorists adjusted parameters within the model Perhaps star formation efficiency was slightly higher or lower than initially assumed, or feedback mechanisms worked differently than expected. But the fundamental timeline remained intact. Galaxies couldn't form too early because the universe needed time for structures to assemble. JWST was expected to refine this picture, to see slightly farther and with greater clarity, but not to overturn it. That confidence lasted until the telescope's first deep-field images arrived, revealing galaxies where none should exist, too many, too bright, and too mature for the universe's age. JADESGSZ 130, the galaxy that shouldn't exist. When astronomers using the James Webb Space Telescope analyzed data from the JWST Advanced Deep Extragalactic Survey, JADES for short, they encountered an object that made them reconsider everything they thought they knew about early galaxy formation. Designated JADESGSZ 130, this galaxy appeared at a redshift of 13.2, corresponding to just 325 million years after the Big Bang. At first glance, detecting a galaxy at this epoch seemed impressive but not shocking. JWST was designed to see farther than Hubble, after all. But as researchers examined the galaxy's properties in detail, the real surprise emerged. This wasn't a faint, tiny proto-galaxy struggling to form stars. It was bright, relatively large, and showed clear signs of an established stellar population already billions of years into its evolution, an impossibility according to standard timeline models. The galaxy's brightness stood out immediately. With an apparent magnitude measured in JWST's NIRCam instrument, JADESGSZ 130 shone far more brightly than theoretical models predicted possible at such early times. Brightness in astronomy correlates with either stellar mass or extreme star formation activity. For this galaxy to appear so bright at such a distance required either a massive population of stars already formed or an extraordinarily intense burst of star formation occurring when we observe it. Either scenario created problems. If the stellar population was already massive, perhaps 100 million to 1 billion solar masses, then stars must have formed much earlier and more efficiently than theory allowed. If instead the brightness came from intense star formation, the rate would need to be so high that it violated constraints on how quickly gas could collapse and convert into stars. Spectroscopic analysis revealed the galaxy's redshift with high confidence. When light travels through expanding space, its wavelengths stretch in proportion to the universe's expansion. This cosmological redshift provides a direct measurement of distance and look-back time. JADESGSZ 130 spectrum showed the characteristic Lyman alpha emission line produced by hydrogen atoms shifted from its rest wavelength of 121.6 nanometers to over 1,700 nanometers. In the infrared, this enormous shift placed the galaxy firmly in the epoch when the universe was barely 2.5% of its current age. At that time, according to models, only the first generation of stars should have been forming, not complete galaxies with organized structures and multiple stellar populations. The galaxy's morphology presented another puzzle. While not perfectly resolved in JWST images due to its extreme distance, JADESGSZ 130 showed spatial extent and structure rather than appearing as a point source. This meant it had already assembled a significant amount of mass across a measurable physical size, perhaps 1,000 to 2,000 light-years in diameter. For comparison, the Milky Way's disk spans 100,000 light-years. So this early galaxy was far smaller. But for such a young universe, Even a compact galaxy of this size required time to assemble. Dark matter halos had to collapse. Gas had to cool and flow inward. Stars had to form, and the resulting structure had to settle into a coherent configuration. Each process took tens to hundreds of millions of years in simulations. How could all this happen in just 325 million years? Color measurements from JWST's multiple infrared filters revealed something equally surprising. The galaxy's spectral energy distribution, the way its brightness varies with wavelength, indicated the presence of dust. Dust consists of heavier elements like carbon, silicon, and iron, formed in stellar cores and released through supernova explosions. The presence of detectable dust meant that multiple generations of stars must have already lived and died, seeding the interstellar medium with these heavy elements. Population 3 stars, the first generation, made purely of hydrogen and helium, leave no dust when they explode. Only later generation stars containing metals can produce dusty remnants. This meant JADESGSZ130 had undergone significant chemical evolution, with stars forming, living, exploding, and enriching the gas that formed subsequent stars. All this complex stellar archaeology occurring in just 325 million years seemed impossibly rushed. Estimates of the galaxy's stellar mass ranged from several tens of millions to possibly over 100 million solar masses, depending on assumptions about star formation history and dust extinction. Even taking the conservative lower estimate created problems. To build tens of millions of solar masses of stars in just 325 million years required an average star formation rate of at least 0.1 solar masses per year, sustained continuously from very early times. But the first stars couldn't form until at least 100 to 200 million years after the Big Bang, when dark matter halos reached sufficient density. This left only 125 to 225 million years to accomplish all the galaxy's assembly. The required star formation efficiency, the fraction of available gas converted into stars, would need to be far higher than observed in local galaxies or predicted by simulations. The Discovery team carefully checked for possible errors. Could the redshift measurement be wrong, placing the galaxy closer than it appeared? Multiple spectroscopic lines confirmed the redshift independently, eliminating this possibility. Could dust or gravitational lensing artificially boost the galaxy's apparent brightness? No evidence of a foreground galaxy or cluster capable of lensing appeared in the field, and the dust signature, while present, wasn't extreme enough to explain the brightness through scattered light. Could contamination from a foreground object at lower redshift mimic a distant galaxy's spectrum? Deep imaging showed no such contaminating sources. Every check confirmed what the data indicated: an unexpectedly mature galaxy existing far earlier than standard models predicted possible. JADESGSZ130 wasn't unique either. Several other similarly problematic galaxies appeared in the same survey, suggesting this represented a real population rather than a single anomaly. How redshift reveals cosmic distance. Understanding why JADESGSZ130's discovery is so shocking requires understanding redshift, the fundamental tool astronomers use to measure distances to faraway galaxies. Redshift is one of astronomy's most elegant concepts, connecting the expansion of the universe directly to observable changes in light. When a galaxy's light travels through expanding space toward Earth, that expansion stretches the light's wavelengths, shifting them toward the red end of the electromagnetic spectrum. The amount of stretching reveals how much the universe has expanded since the light began its journey, which in turn reveals the galaxy's distance and the era when the light was emitted. This simple principle unlocks the entire cosmic timeline. The physics behind redshift stems from general relativity. Einstein's equations predict that space itself can expand, and observations by Edwin Hubble in the 1920 seconds confirmed this prediction. When space expands, everything embedded in it moves apart, not through space, but because space itself is stretching. Light waves travelling through this expanding space get stretched along with it. A photon emitted with a wavelength of 500 nanometers green light might arrive at Earth with a wavelength of 1000 nanometers infrared because space doubled in size during the photon's journey. Astronomers define redshift mathematically as Z equals lambda observed minus lambda rest divided by lambda rest, where lambda represents wavelength. A redshift of Z equals 1 means wavelengths have doubled, corresponding to the universe being half its current size when the light was emitted. Measuring redshift requires identifying known spectral features in a galaxy's light. Every element produces characteristic emission or absorption lines at specific wavelengths when electrons transition between energy levels. Hydrogen, for instance, produces the Lyman alpha line at 121.6 nanometers in the ultraviolet. Oxygen produces lines at 500.7 and 495.9 nanometers in the visible spectrum. These wavelengths are invariant. They're determined by quantum mechanics and are identical everywhere in the universe. By comparing the observed wavelengths of these lines in a distant galaxy's spectrum to their rest wavelengths measured in laboratories on Earth, astronomers calculate exactly how much space has stretched. If the Lyman alpha line appears at 1,700 nanometers instead of 121.6 nanometers, the redshift is approximately 13, meaning space has expanded by a factor of 14 since the light was emitted. Converting redshift to distance and look-back time requires applying cosmological models. The relationship isn't linear because the universe's expansion rate has changed over cosmic history. Shortly after the Big Bang, expansion was faster due to the density of matter and radiation. As the universe expanded, matter density decreased, causing expansion to slow. But roughly 5 billion years ago, dark energy began dominating, causing expansion to accelerate again. To calculate distance from redshift, astronomers input the measured Z value into equations from general relativity, along with parameters describing the universe's composition, the density of matter, dark energy, and radiation. The current standard cosmological model, Lambda-CDM, provides these parameters with high precision thanks to measurements from the cosmic microwave background and large galaxy surveys. For JADESGSZ 130 at redshift 13.2, the calculation reveals remarkable numbers. The galaxy's light has travelled 13.5 billion years to reach us, meaning we see it as it appeared just 325 million years after the Big Bang. The light travel distance is 13.5 billion light-years. But the galaxy's current proper distance, accounting for space expansion during the light's journey, is approximately 33 billion light-years. This seems to violate the cosmic speed limit, since the universe is only 13.8 billion years old, but there's no contradiction. Space itself can expand faster than light because no information or matter travels faster than light through space. The galaxy isn't moving away superluminally. Rather, space between us and the galaxy stretched during the 13.5 billion years the light was travelling. When the light was emitted, the galaxy was roughly 3 billion light-years away. But expansion pushed it farther during the photon's journey. high redshift measurements became possible only with infrared space telescopes. As redshift increases, light originally emitted in the ultraviolet and visible spectrum shifts into the infrared. A galaxy at z=10 emits most of its light in the ultraviolet, but by the time it reaches Earth, that light arrives at near-infrared wavelengths around 1 to 2 micrometers. JWST's instruments detect wavelengths from 0.6 to 28 microns, perfectly suited for observing galaxies at redshifts between 6 and 15, the era when the first galaxies formed. Hubble, limited to wavelengths shorter than 1.6 microns, could reach only to redshift 11 at best, and only for the brightest objects. JWST's infrared capabilities pushed this boundary dramatically, revealing galaxies at redshifts exceeding 13 with relative ease. Confirming redshifts requires spectroscopy spreading light into its component wavelengths to identify emission and absorption lines. JWST carries spectrographs like NIRSpec that accomplish this task for faint, distant galaxies. The process isn't simple. At extreme distances, galaxies appear incredibly faint, requiring hours of exposure time to collect enough photons for analysis. Their spectra often show only 1 or 2 prominent lines, making redshift determination challenging. Astronomers must rule out alternative explanations. Could the lines come from a closer galaxy at lower redshift, where different transitions produce similar wavelengths? Multiple spectral features observed simultaneously eliminate such ambiguities. For JADE SGSZ130, the detection of multiple hydrogen lines all shifted consistently confirmed the redshift measurement beyond reasonable doubt, establishing the galaxy's extraordinary distance and age. The star formation problem in the early universe. Building stars isn't simple, especially in the early universe where conditions were far from ideal. Modern star formation theory, refined through decades of observations in nearby galaxies, describes a specific sequence of events. Cold molecular gas clouds collapse under gravity until their cores reach densities and temperatures sufficient to ignite nuclear fusion. The process converts roughly 1 to 3% of available gas into stars per million years under normal circumstances. Higher efficiency encounters obstacles. Radiation pressure from newly formed stars heats surrounding gas, driving it outward and halting further collapse. Supernova explosions from massive stars inject enormous energy, creating expanding shockwaves that further disrupt star formation. These feedback mechanisms regulate how quickly galaxies can build stellar populations, preventing runaway star formation that would consume all available gas in a cosmic instant. In the early universe, star formation faced even greater challenges. The first dark matter halos, while gravitationally dominant, were relatively small, perhaps a few 100 million solar masses. These shallow gravitational wells struggled to retain gas heated by the first supernovae. When a massive population 3 star exploded, the energy released could eject most or all of the gas from its host halo, effectively shutting down star formation. Computer simulations show that many early halos experienced sporadic, episodic star formation rather than continuous production. They would form a few stars, those stars would explode, the gas would get ejected, then millions of years would pass before new gas accreted from the intergalactic medium, allowing another brief burst. This stop and start pattern severely limited how quickly stellar mass could accumulate. The gas itself presented problems. In the early universe, hydrogen and helium dominated overwhelmingly, roughly 76% hydrogen and 24% helium by mass, with only trace amounts of lithium. heavier elements didn't exist yet. This pristine composition made cooling difficult. When gas collapses under gravity, gravitational potential energy converts to heat, raising the temperature. For collapse to continue, this heat must radiate away, allowing the cloud to shrink further. In modern molecular clouds, elements like carbon and oxygen form molecules such as carbon monoxide that efficiently radiate energy in the infrared. But primordial gas lacked these elements. Only molecular hydrogen could provide cooling, and it's far less efficient. This inefficiency meant gas had to reach higher densities and temperatures before fragmenting into stars, favouring the formation of very massive stars rather than the diverse stellar populations we see today. These massive population 3 stars created another problem. They died quickly. A star 100 times the Sun's mass lives only a few million years before exploding as a supernova, nearly instantaneous on cosmic timescales. When multiple such stars formed in the same halo, their collective supernovae could occur within a few million years of each other, releasing staggering amounts of energy in a brief period. Simulations show this creates a phenomenon called blowout, where the combined feedback not only ejects gas from the host halo, but also heats and ionizes gas in surrounding halos, suppressing star formation across larger regions. A single vigorous burst of population 3 star formation could sterilize an entire region of space, delaying subsequent generations for hundreds of millions of years. Another complication involved the chemical evolution timeline. The first stars contained essentially zero metals, the astronomical term for elements heavier than helium. When they exploded, they enriched their surroundings with carbon, oxygen, nitrogen, silicon, iron, and other elements forged in their cores and during the supernova itself. This enrichment was crucial because it enabled more efficient gas cooling in subsequent generations, allowing smaller, longer-lived stars to form. But the enrichment process was slow and uneven. Gas ejected from a halo didn't immediately settle into nearby halos. It scattered across large volumes, mixing gradually with pristine gas over tens to hundreds of millions of years. Observations suggest metallicities remained extremely low, perhaps 1/100th to 1,000th of the Sun's metal content, until several 100 million years after the Big Bang. Given these obstacles, standard models predicted gradual stellar mass buildup in early galaxies. A typical halo at 200 million years might contain a few 100,000 solar masses of stars at most. By 400 million years, repeated accretion and star formation could boost this to a few million solar masses. By 600 million years, the largest systems might reach tens of millions of solar masses. 100 million solar mass galaxies shouldn't appear until 800 million to 1 billion years, when sufficient time had passed for multiple generations of star formation, metal enrichment, and gas accretion cycles. These predictions weren't arbitrary. They emerged from detailed simulations matching observations of stellar populations, chemical abundances, and galaxy properties at lower redshifts where measurements were secure. Yet JADESGS Z130 contained an estimated 100 million solar masses or more at just 325 million years. Achieving this required star formation rates and efficiencies far exceeding standard predictions. If star formation began at 200 million years optimistically early, the galaxy had only 125 million years to build its stellar population. That demanded an average star formation rate of at least 0.8 solar masses per year, sustained continuously. For comparison, the Milky Way currently forms about 1.5 solar masses per year, but it has far more gas and a much deeper gravitational well. Early halos with weaker gravity and less gas shouldn't sustain such high rates. Even more troubling, the galaxy showed evidence of dust and metal enrichment, implying multiple stellar generations had already occurred. This required an even earlier star formation onset, perhaps as early as 150 million years, which seemed physically implausible given the time needed for dark matter halos to collapse and cool primordial gas sufficiently. Breaking the stellar mass growth timeline. Astronomers calculate how galaxies accumulate stellar mass using models that integrate star formation over cosmic time. These models, tested against observations of galaxies at various redshifts, consistently show that stellar mass builds gradually. At any given epoch, a galaxy's stellar mass reflects the balance between star formation, which adds mass, and stellar evolution, which removes mass through supernovae and stellar winds. Early theoretical work by Tinsley, Larson, and others in the 1970 seconds established that galaxies typically convert only a small fraction of their gas into stars per dynamical time, the time it takes for material to orbit once through the galaxy's gravitational potential. This fraction, called the star formation efficiency, rarely exceeds 1 to 3% per dynamical time in local galaxies. The dynamical time itself presents a constraint in the early universe. For a dark matter halo of 100 million solar masses at redshift 13, the dynamical time is approximately 10 million years. With a 2% efficiency, such a halo converts about 2 million solar masses of gas into stars every dynamical time. Over 100 million years, roughly the time available between the first possible star formation at 200 million years and JADESGSZ130's observation at 325 million years. This yields about 20 million solar masses total. Reaching 100 million solar masses would require either a star formation efficiency of 10%, 5 times the typical value, or a halo mass significantly larger than typical at this epoch. Both scenarios conflict with theoretical expectations and observations of lower redshift galaxies. The problem compounds when considering feedback mechanisms. Every massive star releases copious ultraviolet radiation that ionizes and heats surrounding gas. When the star explodes as a supernova, it injects kinetic energy equivalent to 10 to the power of 51 ergs, roughly 100 times the Sun's total lifetime energy output into the interstellar medium. This energy drives powerful winds that expel gas from the galaxy. Observations show that in local dwarf galaxies, supernova feedback can eject 10 to 100 times more gas mass than the mass of stars that formed, effectively self-regulating star formation by removing fuel. If similar feedback operated in early galaxies, accumulating large stellar masses becomes even more difficult. Either feedback was mysteriously weaker in the early universe, or some mechanism continuously replenished ejected gas faster than models predict. One possible solution involves sustained gas accretion from the intergalactic medium. In standard models, halos grow over time by accreting dark matter and gas from surrounding filaments of the cosmic web. This infall gas provides fuel for ongoing star formation. If accretion rates were higher than expected in the early universe, galaxies could sustain elevated star formation rates despite feedback. However, simulations constrain how fast gas can flow onto halos based on the geometry and density of cosmic structure at each epoch. At redshift 13, filaments were thinner and less dense than at later times, limiting accretion rates. Moreover, high accretion rates create another problem. They heat gas through gravitational compression and shocks as it falls into the halo, potentially raising temperatures too high for efficient star formation. Another consideration involves the initial mass function, the distribution of stellar masses formed in each star formation event. In local galaxies, the IMF is well characterized. For every high-mass star, hundreds of low-mass stars form. The high-mass stars produce most of the light but constitute only a small fraction of the stellar mass. If the early universe IMF were top-heavy, forming proportionally more high-mass stars, then the same amount of starlight could correspond to less total stellar mass. This would ease the mass build-up problem. However, a top-heavy IMF exacerbates the feedback problem because high-mass stars produce more energetic supernovae. Additionally, spectroscopic observations of early galaxies haven't shown the extreme emission line ratios that a very top-heavy IMF would produce, suggesting the IMF wasn't radically different from today's. Chemical evolution timescales add another layer to the puzzle. JADESGSZ130's spectrum shows emission lines indicating the presence of elements like oxygen, carbon, and possibly nitrogen elements produced inside stars and released through supernovae. The most massive population 3 stars live only 2 to 3 million years before exploding. Their explosions enrich surrounding gas with metals, but this enriched material must then be incorporated into a new generation of stars. The entire cycle star formation, stellar evolution, supernova, gas mixing, and renewed collapse requires at least 10 to 20 million years minimum, even under optimized conditions. Detecting significant metal enrichment at 325 million years implies this cycle repeated multiple times, requiring star formation to commence by at least 250 million years, perhaps earlier. Each additional constraint tightens the timeline, making the galaxy's existence increasingly difficult to explain within standard frameworks. Dynamical considerations provide yet another test. A galaxy's size and rotation velocity are related to its mass through the virial theorem from classical mechanics. For a galaxy to remain gravitationally bound, its internal motions must balance the inward pull of gravity. Measuring these motions through spectroscopy, observing how emission lines broaden due to Doppler shifts from rotating gas, reveals the galaxy's dynamical mass. If the dynamical mass significantly exceeds the stellar mass, the difference indicates abundant dark matter and gas, which is expected. If the stellar mass approaches or exceeds plausible dynamical mass estimates, something is wrong. Either the mass estimates are incorrect or the system isn't in equilibrium. Initial studies of high redshift galaxies, detected by JWST, suggest their stellar masses often approach a significant fraction of their total halo masses, higher than expected from simulations, suggesting either unusually efficient star formation or systematic errors in mass estimates, the unexpected maturity of early galaxies. When astronomers analysed JADESGSZ130 inches detail, they found indicators of maturity that shouldn't exist so early. Maturity in galactic archaeology refers to several observable properties: the presence of dust, evidence of multiple stellar populations with different ages, organised structures rather than chaotic clumps, and chemical enrichment showing that several cycles of star formation had already occurred. Each of these properties requires time to develop. Dust forms only after massive stars explode, releasing carbon, silicon, and other heavy elements that condense into microscopic grains. Multiple stellar populations imply successive generations separated by millions to tens of millions of years. Organized structures require gravitational relaxation and gas dissipation. processes operating over many dynamical times. Chemical enrichment demands repeated star formation, supernova, and gas recycling cycles. Observing all these features simultaneously in a galaxy seen just 325 million years after the Big Bang was unexpected. The detection of dust was particularly surprising. Dust grains form when atoms of elements like carbon and silicon condense in the cooling ejecta of supernova explosions or in the atmospheres of evolved stars called asymptotic giant branch stars. Population 3 stars, the first generation, can produce some dust, but observational evidence suggests population 3 dust production is relatively inefficient and produces distinct grain compositions. The dust detected in high redshift galaxies like JADESGSZ130 shows properties more consistent with evolved stellar populations, later generation stars that formed from gas already enriched by previous pace, supernovae. This implied that by 325 million years, at least 2 or 3 stellar generations had formed, lived, and died. The earliest generation might have begun at 150 to 200 million years, lived 2 to 3 million years, exploded, enriched the gas, which then cooled over 10 to 20 million years before forming second-generation stars. Those second-generation stars, including some intermediate mass stars that evolve more slowly, would need another 50 to 100 million years to produce significant dust in their winds and eventual supernovae. Adding these timescales suggested star formation must have begun extremely early, perhaps as early as 100 to 150 million years after the Big Bang, during the final stages of the cosmic dark ages, when the first population 3 stars were just igniting. This pushed the timeline to its absolute physical limits, leaving almost no margin for the slower, more episodic star formation that simulations predicted. Spectroscopic observations revealed additional maturity indicators through emission line ratios. When gas clouds are ionized by ultraviolet radiation from hot stars, they emit characteristic lines at specific wavelengths. The relative strengths of these lines, particularly oxygen, nitrogen, and hydrogen lines, provide diagnostic information about the gas's chemical composition and the properties of the stars ionizing it. JADESGSZ130's spectrum showed line ratios consistent with gas that had been enriched to metallicities of perhaps 10 to 20% of solar values. While still metal poor by modern standards, this was far higher than the essentially zero metallicity of pristine gas. Achieving this enrichment level required substantial stellar mass, perhaps 50 to 100 million solar masses, to have formed, evolved, and exploded as supernovae, distributing their processed elements throughout the galaxy's interstellar medium. The galaxy's morphology, though difficult to resolve at such an extreme distance, provided another clue. Rather than appearing as a single compact blob which might indicate a very young, recently assembled system, JADESGSZ130 showed spatial extension and possible substructure. High-resolution JWST imaging revealed the galaxy spanned approximately 1,000 to 1,500 light-years in diameter, with brightness variations suggesting either multiple star-forming regions or clumps of stars at different evolutionary stages. This spatial complexity indicated that the galaxy had undergone some dynamical evolution. Newly formed galaxies, emerging from the collapse of dark matter halos, typically appear highly irregular and clumpy, with star formation concentrated in dense, chaotic knots. Over time, typically hundreds of millions of years, gravitational interactions and gas dissipation smooth these irregularities, creating more organized structures. Finding organized structure at 325 million years suggested accelerated evolution compared to theoretical predictions. Color measurements from JWST's multiple infrared filters revealed another maturity indicator, a rest frame optical break. This refers to a sudden decrease in brightness at wavelengths corresponding to the Balmer break at 365 nanometers in the galaxy's rest frame, caused by absorption in the atmospheres of older stars. The Balmer break becomes prominent in stellar populations that have aged for at least 100 to 300 million years, when massive blue stars have died and intermediate age stars dominate the light. Detecting this feature in JADES-GSZ-130 implied the presence of stellar populations at least 100 million years old. Since we observe the galaxy at 325 million years of cosmic time, this means star formation must have commenced by 225 million years at the latest, again pushing against the earliest possible times when star formation could have begun. Some researchers propose that gravitational lensing might explain the galaxy's unexpected brightness and apparent maturity. Gravitational lensing occurs when a massive foreground object, another galaxy or cluster, bends and magnifies light from a more distant background source. This natural telescope effect can boost apparent brightness by factors of 2 to 100 or more, making distant galaxies appear brighter and larger than they actually are. If JADES-GSZ-130 were lensed, its intrinsic stellar mass might be significantly lower, perhaps only 10 to 30 million solar masses, which would ease tension with theoretical models. However, careful examination of the field showed no evidence of a massive foreground lensing galaxy or cluster. The absence of multiple images, arcs, or other lensing signatures strongly argued against significant magnification. The galaxy appeared to be genuinely as bright and massive as initial measurements indicated. Alternative explanations involved exotic stellar populations. Some theorists suggested that the first stars might have been even more massive than standard population 3 models predicted, perhaps 500 or 1,000 solar masses, and formed in greater numbers. These hypothetical supermassive stars would have been extraordinarily luminous, potentially producing as much light as an entire small galaxy, while contributing relatively little stellar mass. If a significant fraction of JADES-GSZ-130's light came from such objects, the inferred stellar mass would be overestimated. However, supermassive stars face stability problems. Their intense radiation pressure should blow them apart before they can grow so large, and no observational evidence for their existence has been confirmed. Moreover, supermassive stars would produce distinctive spectral signatures, particularly very strong helium emission lines, which haven't been prominently detected in early galaxy spectra. The discovery of multiple similarly mature galaxies at comparable redshifts strengthen the case that this wasn't a statistical fluke. Within the same JD's survey and contemporaneous JWST programs, like Sears and Glass, astronomers found dozens of galaxies at redshifts between 10 and 14 showing similar properties. Higher stellar masses than expected, evidence of dust and metal enrichment, and organized morphologies. The cumulative number density, how many such galaxies exist per unit volume of space, exceeded predictions from standard Lambda-CDM simulations by factors of 3 to 10, depending on the exact mass and redshift range considered. This systematic excess suggested a fundamental problem rather than measurement uncertainties. Either the simulations were missing physics that accelerates early galaxy formation, or the observational inferences contained systematic errors inflating estimated masses and maturity levels. Reionization and its unexpected timeline. The cosmic reionization epoch represents one of the most significant phase transitions in the universe's history, the transformation of neutral hydrogen filling space back into an ionized plasma. This process began when the first stars and galaxies emitted enough ultraviolet radiation to strip electrons from hydrogen atoms in the intergalactic medium. Standard models predicted reionization commenced around 300 to 400 million years after the Big Bang, proceeded gradually over several hundred million years, and completed by approximately 1 billion years when observations of distant quasars showed the universe was almost fully ionized. The timeline made physical sense. Early star formation was inefficient. Ultraviolet photons struggled to escape dense galaxies, and each ionized region expanded slowly into surrounding neutral gas. Complete reionization required sufficient time for these bubbles to grow, overlap, and fill the universe. JWST observations challenged this comfortable picture. The discovery of numerous bright, actively star-forming galaxies at redshifts 12 to 14, corresponding to 350 to 270 million years after the Big Bang, implied that ionizing photon production began earlier and proceeded more vigorously than predicted. Each massive star produces enormous numbers of ultraviolet photons during its lifetime. A galaxy forming stars at several solar masses per year generates enough ionizing radiation to create a bubble of ionized hydrogen expanding at thousands of kilometers per second. The cumulative effect of hundreds or thousands of such galaxies operating simultaneously could reionize the universe faster than models suggested. Finding mature galaxies at redshift 13 indicated that star formation was already well established by 325 million years, pushing reionization onset backward in time. Observations of the cosmic microwave background provided additional constraints. Detailed maps from the Planck satellite measured the CMB's polarization, the orientation of electromagnetic waves, which is affected when CMB photons scatter off free electrons. By analyzing polarization patterns, researchers calculated the integrated optical depth to reionization, a parameter indicating how many free electrons existed along the line of sight from the early universe to today. Planck's measurements constrained this optical depth, implying that reionization occurred in a specific time frame. If reionization happened too early, the optical depth would be higher than observed. Too late, and it would be lower. The measured value suggested reionization occurred primarily between 400 million and 900 million years, with some contribution possibly extending earlier. Finding significant galaxy populations at 300 million years implied reionization might have begun at the earlier end of this range, or even before. The efficiency of photon escape from early galaxies became crucial. Ultraviolet photons ionize hydrogen, but most are absorbed by neutral hydrogen within the galaxy itself before escaping into intergalactic space. Only photons that escape, characterized by the escape fraction, contribute to reionization. In local star-forming galaxies, escape fractions are typically low, around 1 to 5%, because dense gas surrounding star-forming regions absorbs most ionizing radiation. Theoretical models assumed similar escape fractions in early galaxies. However, if early galaxies had higher escape fractions, perhaps 10 to 30% due to their lower metallicities and less dusty environments, they would more efficiently ionize their surroundings. Some JWST observations hinted at evidence for higher escape fractions in high redshift galaxies, though measuring this parameter directly remains challenging. The morphology and structure of early galaxies also affected reionization. Compact, dense galaxies tend to retain their ionizing photons, while more extended systems with lower surface densities allow photons to escape more easily. Additionally, feedback from supernovae and stellar winds can blow holes in the surrounding gas, creating channels through which ultraviolet radiation streams into intergalactic space. If early galaxies were more prone to such outflows, possibly because their shallower gravitational potentials made gas easier to expel, they could have contributed more efficiently to reionization than their local counterparts. Observations of highly ionized gas moving at high velocities in some early galaxies support this possibility, though the frequency and strength of such outflows remain uncertain. Another factor involved the contribution from faint, low-mass galaxies. Surveys detect only the brightest galaxies at high redshift because fainter ones fall below observational limits. However, models predict that low-mass galaxies too faint for current telescopes to detect individually should be numerous and collectively contribute significantly to reionization. These dwarf galaxies might have higher escape fractions than massive systems because their weaker gravity allows feedback to more easily expel gas, creating pathways for ionizing photons. If the abundance of faint galaxies exceeded predictions, their cumulative ionizing output could explain how reionization proceeded despite uncertainties about massive galaxies' escape fractions. Unfortunately, directly observing these faint populations at redshift 10 and beyond remains beyond current capabilities, leaving their contribution uncertain. The discovery of active galactic nuclei at high redshift added complexity. Some early galaxies host supermassive black holes accreting gas and emitting prodigious amounts of radiation, including ionizing ultraviolet photons. These quasars can ionize surrounding volumes far exceeding what stellar populations alone could accomplish. JWST detected several such systems at redshifts between 8 and 10 earlier than expected. If supermassive black holes formed and grew faster than models predicted, mirroring the surprise of early galaxy maturity, they could have contributed meaningfully to reionization. However, the number density of high redshift quasars appears insufficient to reionize the universe by themselves. They likely played a supporting role alongside star-forming galaxies. Measurements from the 21-centimeter line of neutral hydrogen offered another probe of reionization's timeline, though technical challenges have limited progress. When hydrogen is neutral, it emits faint radio waves at a wavelength of 21 centimeters. During reionization, neutral hydrogen is converted to ionized plasma, eliminating this emission from ionized regions. Radio telescopes like LOFAR, MWA, and HERA are attempting to detect the statistical signature of reionization by observing how 21 centimeter emission varies across the sky and with redshift. Successful detection would reveal when and how quickly reionization occurred, providing crucial independent verification of galaxy-based models. To date, only upper limits have been established, but these limits are beginning to constrain models, suggesting reionization's midpoint occurred between redshift 7 and 9, corresponding to 700 to 550 million years after the Big Bang, consistent with quasar observations. The dark matter halo growth paradox. Dark matter halos the invisible gravitational scaffolding within which galaxies form grow hierarchically through a well-understood process. Small halos form first, then merge to create progressively larger structures. This hierarchical assembly is one of the most robust predictions of the Lambda-CDM cosmological model, confirmed by observations of galaxy clustering, gravitational lensing, and the cosmic microwave background. The model predicts how many halos of each mass should exist at any cosmic epoch and how quickly they should grow through accretion and mergers. These predictions constrain when galaxies of various masses can appear because a galaxy's mass cannot exceed its host halo's ability to retain baryonic matter. At redshift 13, corresponding to 325 million years after the Big Bang, Lambda-CDM simulations predict that dark matter halos have only recently begun to collapse into bound structures. The most massive halos at this epoch should contain approximately 1 to 3 billion solar masses of total mass, including both dark matter and baryonic matter. Baryons constitute roughly 16% of this total mass, based on the cosmic baryon fraction measured from the CMB. This means a massive halo at redshift 13 contains perhaps 150 to 500 million solar masses of baryonic matter gas and potentially stars. However, not all this baryonic matter resides within the halo. Much remains in the intergalactic medium or in surrounding filaments. Moreover, star formation efficiency is typically only 1 to 10%, meaning the stellar mass should be 1 to 10% of the baryonic mass. By this accounting, a typical massive halo at redshift 13 should contain at most 5 to 50 million solar masses of stars, significantly less than the 100 million plus solar masses estimated for JADES GSZ 130. Resolving this discrepancy requires either that early halos were more massive than simulations predict, or that they converted baryons into stars far more efficiently. The first option encounters problems because halo masses are tightly constrained by cosmological parameters. The matter-power spectrum, the distribution of density fluctuations as a function of scale, is precisely measured from CMB observations and large-scale structure surveys. This power spectrum determines how quickly halos of different masses collapse. Increasing halo masses at redshift 13 requires modifying fundamental cosmological parameters like the matter density or the amplitude of initial fluctuations. Such changes would affect predictions at all redshifts, potentially breaking agreement with observations at lower redshifts where models currently work well. No simple adjustment to standard parameters can boost high redshift halo masses without creating conflicts elsewhere. The second option, higher star formation efficiency, faces its own challenges. In local galaxies, star formation efficiency is regulated by feedback, radiation pressure, stellar winds, and supernova explosions heat and expel gas, preventing runaway star formation. These feedback mechanisms should operate even more effectively in early galaxies because their shallower gravitational potentials make gas easier to expel. If anything, star formation efficiency should be lower in early halos, not higher. Achieving efficiencies of 20 to 50% necessary to explain observed stellar masses requires suppressing feedback or enhancing star formation through mechanisms not included in standard models. Some possibilities include more efficient gas cooling at high densities, reduced feedback efficiency due to lower metallicities, or continuous rapid gas accretion that replenishes ejected material faster than it can be removed. Another consideration involves the timing of halo assembly. Halos don't reach their final mass instantaneously. They grow gradually through accretion and mergers over hundreds of millions of years. At redshift 13, most halos are still in early assembly phases. They might have assembled significant fractions of their mass only in the preceding 50 to 100 million years. If galaxy formation requires time for gas to settle into the halo, cool, and collapse into stars, then even if star formation commenced immediately upon halo formation, insufficient time exists to build large stellar masses. This timing problem becomes especially severe for galaxies showing signs of multiple stellar populations and chemical enrichment, which require successive generations of star formation separated by tens of millions of years. Some researchers proposed that rare, high-density peaks in the primordial matter distribution statistical outliers in the initial fluctuation field could host unusually massive halos at early times. The theory of Gaussian random fields predicts that rare, high-amplitude fluctuations exist, and in these special locations, halos collapse earlier and grow faster than in typical regions. Identifying such rare peaks in simulations shows they can host halos perhaps 2 to 3 times more massive than typical for their redshift. While helpful, this factor isn't sufficient to explain the most massive early galaxies observed by JWST. Moreover, these rare peaks are extremely uncommon. The survey volumes covered by JWST programs should contain only a few such regions, yet dozens of problematic galaxies have been found, suggesting they aren't rare statistical flukes. The possibility of modified gravity theories arose in discussions, though most physicists consider this unlikely. If gravity behaves differently from general relativity's predictions on cosmological scales, structure formation could proceed differently than Lambda-CDM predicts. Certain modified gravity theories predict enhanced gravitational clustering on specific scales, potentially accelerating halo collapse. However, these theories face severe constraints from other observations, including gravitational wave detections, solar system tests, and galaxy cluster dynamics. Most modified gravity proposals, designed to explain cosmic acceleration without dark energy, produce predictions inconsistent with multiple independent datasets. Invoking modified gravity to solve the early galaxy problem would likely create worse problems elsewhere, making this an unattractive solution. A more conservative possibility involves uncertainties in converting observed light into stellar mass estimates. Inferring a galaxy's stellar mass from its brightness requires assumptions about the stellar population, the ages of stars, their metallicity, the initial mass function, and the amount of dust obscuring light. Different assumptions can change mass estimates by factors of 2 to 5. If early galaxies have stellar populations systematically different from template assumptions, perhaps more top-heavy initial mass functions producing very luminous massive stars, their true stellar masses could be significantly lower than initial estimates suggested. Ongoing spectroscopic observations are testing this possibility by measuring spectral features sensitive to stellar population properties. Early results suggest some reduction in estimated masses is warranted, but probably not enough to fully resolve the tension with theoretical predictions. Challenging the Lambda-CDM model. The Lambda-CDM model has reigned as the standard cosmological framework for over 2 decades, successfully explaining observations from the cosmic microwave background, galaxy surveys, gravitational lensing, and the expansion history of the universe. Lambda represents dark energy, the mysterious force causing accelerated cosmic expansion, while CDM stands for cold dark matter, the invisible mass dominating gravitational dynamics. Together with general relativity and a handful of measured parameters, Lambda-CDM makes precise predictions about structure formation throughout cosmic history. The model's success has been remarkable. It correctly predicts the universe's age, geometry, composition, and the statistical properties of galaxies and clusters across cosmic time. Yet JWST's discovery of unexpectedly mature galaxies at extreme redshifts represents a potential crack in this well-tested edifice. The tension manifests in the abundance of bright, massive galaxies at redshifts above 10. Lambda-CDM predicts the number density galaxies per unit volume of massive systems at high redshift, based on the rate at which dark matter halos collapse and merge. Simulations like Illustris, Eagle, and the Millennium series track billions of particles representing dark matter and gas, following their evolution from shortly after the Big Bang through the present day. These simulations incorporate detailed physics, gas cooling, star formation, supernova feedback, black hole growth, and more. When run with Lambda-CDM parameters measured from the CMB and other observations, they predict specific numbers of galaxies at each mass and redshift. At redshift 13, simulations predict perhaps 1 to 10 galaxies with stellar masses exceeding 100 million solar masses per cubic gigaparsec, a volume containing roughly 100 million cubic light-years. Early JWST surveys have already covered volumes comparable to or larger than those simulated, and the observed number of massive high redshift galaxies appears elevated, perhaps 3 to 10 times higher than predictions, depending on exact selection criteria and mass estimates. This excess isn't enormous. Some previous observational puzzles in cosmology involve discrepancies of factors of 100 or more, but it's statistically significant given the sample sizes and persists across multiple independent surveys. If confirmed with refined mass estimates and larger samples, this excess would indicate either missing physics in galaxy formation models or tension with Lambda-CDM's predictions for early structure formation. Several model components could potentially explain the discrepancy without abandoning Lambda-CDM. First, subgrid physics, the simplified prescriptions for processes occurring below simulation resolution, might inadequately capture early universe conditions. Simulations cannot resolve individual stars or even small molecular clouds. They must use approximate recipes for star formation and feedback calibrated against local observations. If conditions in the early universe differed significantly from today, perhaps star formation proceeded more efficiently due to higher gas densities and less metal enrichment. These prescriptions might fail. Recalibrating them to match JWST observations could resolve the tension while preserving Lambda-CDM's cosmological framework. However, any recalibration must avoid breaking agreement with observations at lower redshifts, where simulations currently perform well, making this a delicate balancing act. Second, the treatment of feedback could be incorrect. Most simulations include feedback from supernovae and stellar winds, but implementing it accurately is notoriously difficult. Feedback operates on scales of parsecs to kiloparsecs, small compared to the hundreds of megaparsecs covered by cosmological simulations. Approximations are necessary, and different simulation groups use different recipes, producing somewhat different results. If feedback was weaker in the early universe, perhaps because low metallicity gas and stars produced less energetic winds, then more gas could have converted into stars, boosting early stellar masses. Some theoretical work suggests that supernova feedback becomes less efficient in dense, rapidly star-forming environments because the gas density is too high for expanding supernova remnants to sweep up and expel material effectively. If early galaxies were denser than local counterparts, this could naturally lead to enhanced star formation. Third, black hole feedback might differ from current implementations. Supermassive black holes regulate galaxy growth in the present-day universe by heating and ejecting gas through jets and radiation pressure, preventing it from forming stars. Simulations tuned to reproduce local galaxy properties include prescriptions for this so-called AGN feedback. However, how black holes formed and grew in the early universe remains poorly understood. If supermassive black hole seeds formed earlier or grew faster than models assume, another JWST surprise, then AGN feedback might have operated differently at high redshift. Alternatively, if black holes were less massive or less active at early times, their feedback would be weaker, allowing more vigorous star formation. Determining which scenario applies requires observations constraining black hole masses in high redshift galaxies. Observations JWST is beginning to provide through detection of broad emission lines characteristic of accreting black holes. Fourth, initial conditions, the density fluctuations present at the end of inflation, could be slightly different from Lambda-CDM's standard assumptions. The model assumes Gaussian random fluctuations with a power law power spectrum characterized by measured parameters. Small deviations from these assumptions, such as primordial non-Gaussianity or running of the spectral index, could enhance structure formation at specific scales and times. These modifications are constrained by CMB observations, but retain some freedom. Fine-tuning such parameters to boost high redshift galaxy abundance without affecting lower redshift observations or CMB predictions is possible in principle, though it would require specific, perhaps contrived, adjustments. Most cosmologists prefer explanations involving uncertain galaxy formation physics over modifying well-constrained cosmological parameters. More radical solutions question Lambda-CDM's foundations. If dark matter is warmer than assumed, with particles moving at higher velocities, structure formation would be suppressed on small scales, but potentially enhanced on larger scales at early times. Warm dark matter models have been proposed to explain other observations, particularly the abundance of satellite galaxies around the Milky Way, but face constraints from gravitational lensing and other tests. Alternatively, if dark energy evolves with time rather than remaining constant, the expansion history could differ from standard predictions, altering when structures collapse. Early dark energy models proposed that dark energy was significant in the early universe, not just recently. Such models could accelerate structure formation by changing the background expansion rate, though they face their own observational challenges. Some physicists even suggested revisiting modified gravity theories that eliminate dark matter or dark energy entirely. The most developed alternative, modified Newtonian dynamics or MOND, successfully explains galaxy rotation curves without dark matter but struggles to account for galaxy clusters and the CMB without additional assumptions. Extending MOND to cosmological scales through relativistic theories like TVES has produced limited success, and most of these theories fail tests from gravitational wave observations. Nonetheless, persistent tensions between observations and Lambda-CDM, not just early galaxy abundances, but also the Hubble tension concerning the expansion rate's precise value, have motivated continued exploration of alternatives, however unlikely they may seem. Spectroscopic confirmation and photometric uncertainties. Determining properties of the most distant galaxies relies on two observational techniques: photometry and spectroscopy. Photometry measures a galaxy's brightness through various filters covering different wavelength ranges, producing a spectral energy distribution, essentially a low-resolution spectrum, showing how brightness varies with wavelength. Spectroscopy spreads light into a continuous spectrum or identifies individual emission and absorption lines, providing detailed information about redshift, chemical composition, gas kinematics, and stellar populations. For extremely faint, distant galaxies, obtaining spectroscopy requires many hours of observation time, so initial surveys rely primarily on photometry to identify candidates, followed by spectroscopic confirmation for the most interesting objects. Photometric redshift estimates depend on template fitting. Astronomers compare observed photometry to libraries of template spectra representing galaxies with various stellar populations, dust contents, and redshifts. The template producing the best match indicates the galaxy's likely properties. This method works reasonably well for relatively nearby galaxies where many photometric points sample the spectrum and distinctive features like the 4000 angstrom break or Lyman break are clearly detected. However, at very high redshifts, galaxies are extremely faint, photometry becomes noisy, and degeneracies arise different combinations of redshift, age, dust, and stellar population can produce similar observed colours. A galaxy at redshift 13 with little dust might look similar to a lower redshift galaxy at redshift 2 with substantial dust. Distinguishing between these scenarios requires either spectroscopy or very precise multiband photometry with excellent signal-to-noise ratios. Early JWST results included many photometric candidates at redshifts 10 to 16 that generated excitement but required spectroscopic verification. Some candidates were confirmed JADES-GSZ130, and several others have secure spectroscopic redshifts with multiple detected emission lines. Others were shown to be lower redshift interlopers galaxies at redshift 4 to 6, whose unusual properties caused photometric redshift estimates to fail. These failed high redshift candidates typically involve dusty, highly star-forming galaxies, or galaxies with unusual emission line ratios that don't match template libraries well. Each spectroscopic observation refines understanding of which photometric signatures reliably indicate extreme distances, improving future candidate selection. The spectroscopic confirmation process for JADES-GSZ130 involved JWST's NIRSpec instrument, which can observe multiple objects simultaneously using a programmable microshutter array. Observers positioned hundreds of tiny shutters to admit light from selected galaxies while blocking light from others, allowing efficient spectroscopy of numerous targets. JADES-GSZ130's spectrum showed clear detection of the Lyman alpha emission line at 1730 nanometers, indicating redshift 13.2, along with tentative detections of other hydrogen lines consistent with this redshift. The Lyman alpha line arises when hydrogen atoms transition from their first excited state to the ground state, emitting a photon at 121.6 nanometers in the rest frame. In extremely distant galaxies, this line shifts into the near-infrared, where JWST's instruments achieve peak sensitivity. However, the Lyman alpha line carries complications at high redshift. As the line's wavelength passes through the intergalactic medium, any neutral hydrogen along the line of sight absorbs photons, attenuating the line's strength. During the reionization epoch, when substantial neutral hydrogen existed, Lyman alpha photons faced severe absorption, and the line could be completely suppressed. Detecting Lyman alpha at redshift 13.2 suggested either that reionization had progressed significantly by that time, creating ionized channels through which photons could escape, or that the galaxy resided in a locally ionized bubble large enough that Lyman alpha photons redshifted out of the line center before encountering significant neutral hydrogen. Either interpretation provided insights into reionization state, but introduced uncertainty about the galaxy's environment and whether it was representative of typical conditions at that epoch. Alternative emission lines provided additional redshift confirmation. Hydrogen produces a series of lines, the Balmer series in the visible and Paschen series in the infrared, that shift into JWST's detection range at high redshift. Detecting multiple lines simultaneously yields robust redshift measurements because the wavelength ratios between lines are fixed by atomic physics. For JADESGSZ130, tentative detections of the H-alpha line at 656.3 nanometers rest wavelength shifted to approximately 9.3 micrometers observed wavelength, supported the redshift estimate. Similarly, oxygen emission lines, particularly the doublet at 372.7 and 372.9 nanometers, shift into observable wavelengths and provide chemical composition information. The strength of oxygen lines relative to hydrogen indicates the gas metallicity, the abundance of elements heavier than helium, revealing how many generations of stars had enriched the interstellar medium. Systematic uncertainties in spectroscopic measurements arise from several sources. Faint emission lines near the detection limit might represent noise fluctuations rather than real features, necessitating careful statistical analysis. Sky background subtraction, removing contamination from Earth's atmosphere, zodiacal light, and diffuse galactic emission becomes critical when the galaxy signal is weak. Wavelength calibration must be precise because small errors shift lines, altering inferred redshifts, and template-dependent analyses used to estimate stellar masses, ages, and dust content from spectral features carry model uncertainties depending on assumptions about stellar population synthesis, dust properties, and emission line physics. Different research groups analyzing the same data with different methods can derive stellar mass estimates differing by factors of 2 to 3, though redshift measurements are typically more robust. The role of dust in early universe observations. Dust, microscopic solid particles composed of carbon, silicates, and other refractory materials, plays an outsized role in interpreting observations of distant galaxies. Dust absorbs ultraviolet and visible light, converting it to infrared emission, thereby altering observed spectral energy distributions and complicating estimates of stellar masses, star formation rates, and ages. In nearby galaxies, dust's effects are well characterized through multi-wavelength observations spanning ultraviolet to far infrared, allowing accurate corrections. In the early universe, dust's presence was initially surprising because dust requires heavy elements produced by stars. Finding substantial dust in galaxies seen only a few 100 million years after the Big Bang implies rapid stellar evolution and metal enrichment, adding to evidence for accelerated galaxy evolution. Dust forms through several pathways. Core collapse supernovae, explosions of massive stars produce dust grains, condensing in expanding ejecta as temperatures cool below 1000 to 2000 Kelvin. This supernova dust is believed to be the dominant source in the early universe before other mechanisms became efficient. Asymptotic giant branch stars evolved intermediate mass stars with extended, cool atmospheres, also produce dust. But these stars require hundreds of millions of years to reach this evolutionary phase, making them unlikely contributors in the youngest galaxies. Grain growth in the interstellar medium, where atoms accrete onto existing dust particles, enhances dust masses over time, but requires seed grains to nucleate first. The rapid appearance of dust in early galaxies points toward efficient supernova production as the primary mechanism. Detecting dust directly is challenging. Cold dust emits primarily in the far infrared and sub-millimeter wavelengths, difficult to observe from the ground due to atmospheric absorption and requiring space telescopes or high-altitude observatories. At high redshift, dust emission shifts into the millimeter and radio wavelengths accessible to ground-based telescopes like ALMA. Observations with ALMA have detected dust continuum emission from a handful of galaxies at redshifts 6 to 8, confirming dust masses reaching tens of millions of solar masses comparable to dust content in local galaxies, despite the cosmic youth. Extending such observations to redshift 13 remains extremely difficult because dust emission becomes very faint and requires prohibitively long integration times with current facilities. Indirect dust detection relies on its effect on stellar light. Dust preferentially absorbs shorter wavelengths, ultraviolet and blue light, while allowing longer wavelengths, red and infrared, to pass more freely. This selective absorption reddens galaxy colours, making them appear redder than their intrinsic stellar populations would predict. Measuring this reddening requires comparing observed colours to models of dust-free stellar populations. If a galaxy appears redder than expected, dust extinction provides one explanation. However, degeneracies arise. An intrinsically red stellar population containing old stars can mimic the colours of a young blue population reddened by dust. Breaking this degeneracy requires spectroscopy to identify age-sensitive features or far-infrared observations to detect reprocessed dust emission, confirming dust's presence independently. For JADESGSZ130, evidence for dust came from multiple indicators. The galaxy's spectral energy distribution showed less ultraviolet emission than expected for a purely young stellar population, suggesting dust absorption. Emission line ratios indicated elevated metallicity, implying sufficient supernovae had occurred to produce both metals and dust. And the inferred stellar mass, when corrected for dust extinction, required assuming significant dust to reconcile observed brightness with the expected luminosity of the stellar population. Different research groups adopted different dust assumptions, leading to stellar mass estimates ranging from 50 million to over 200 million solar masses, a factor of 4 uncertainty dominated by dust corrections. This uncertainty highlights a critical challenge. Estimating dust content requires assumptions about dust properties, grain size distributions, chemical composition, and geometry of dust relative to stars calibrated from local galaxy observations. If dust in the early universe had different properties from local dust, corrections would be systematically biased. For example, supernova-produced dust might have different grain sizes or compositions than dust in evolved stellar systems, affecting how efficiently it absorbs and scatters light at different wavelengths. Observations suggest that high redshift dust is warmer than local dust, indicating it is heated by more intense radiation fields in compact, star-forming galaxies, but whether its intrinsic properties differ remains uncertain. Some researchers argued that the unexpectedly high stellar masses inferred for early galaxies might partially result from overestimating dust content. If less dust exists than assumed, the same observed brightness corresponds to less stellar mass, easing tension with theoretical predictions. Testing this hypothesis requires far-infrared and sub-millimeter observations, detecting thermal dust emission directly, providing dust mass measurements independent of stellar population models. Planned observations with future facilities, like the Atacama Large Aperture Sub-Millimeter Telescope, will provide such measurements, potentially resolving whether dust uncertainties significantly contribute to the early galaxy problem. Stellar population synthesis models and their limitations. Translating observed light from galaxies into physical properties like stellar mass, age, and star formation rate requires stellar population synthesis models, sophisticated computer codes that predict how populations of stars with various ages, metallicities, and initial mass functions produce light at different wavelengths. These models begin with stellar evolution theory, tracking how stars of different masses evolve from birth through various stages. Main sequence, red giant, supernova, calculating their luminosities, temperatures, and spectra at each stage. By combining thousands of stellar evolutionary tracks weighted by the initial mass function, the distribution of stellar masses at birth, and integrating over time, the models produce synthetic spectra for stellar populations of any age and composition. The most widely used synthesis codes include FSPS, BC3, PEGACE, and BPAS, each implementing slightly different assumptions about stellar evolution physics, mass loss rates, binary star interactions, and spectral libraries. When applied to the same observed galaxy, these different codes can produce stellar mass estimates differing by factors of 1.5 to 3, illustrating inherent systematic uncertainties. The uncertainties arise because stellar evolution theory, while well tested for nearby stars, involves complex physics that remains imperfectly understood, particularly for massive stars, evolved phases, and extreme metallicities far from solar values. In the early universe, where metallicities are very low and stellar populations are young, these uncertainties amplify because calibrations rely on solar neighborhood stars that differ significantly from early cosmic conditions. The initial mass function constitutes a major uncertainty source. The IMF describes how many stars form at each mass, typically parameterized by power laws with measured slopes. Locally, the Salpeter or Chabrier IMFs provide good fits, predicting that for every high-mass star formed, hundreds of low-mass stars emerge. However, whether this IMF is universal across cosmic time and environments remains debated. Theoretical arguments suggest that the IMF might be top-heavy in the early universe, forming proportionally more massive stars because low metallicity gas fragments less efficiently during collapse, favoring formation of larger clumps. A top-heavy IMF produces more light per unit stellar mass because massive stars are extremely luminous. If early galaxies had top-heavy IMFs, their true stellar masses would be lower than estimated using standard IMFs, potentially resolving some tension with theoretical predictions. Testing IMF variations observationally is difficult. Direct star counts work only in the nearest galaxies where individual stars are resolved. For distant galaxies, astronomers rely on spectral features sensitive to the IMF's low mass end, such as gravity-sensitive absorption lines in integrated spectra. These features indicate the relative numbers of low-mass versus high-mass stars. Studies of nearby massive elliptical galaxies find evidence for bottom-heavy IMFs in their cores, more low-mass stars than Salpeter predicts, but extending such measurements to high redshift remains beyond current capabilities. Some emission line ratios in early galaxy spectra show patterns potentially consistent with top-heavy IMFs, but alternative explanations involving unusual chemical abundances or high ionization states cannot be excluded. Definitive constraints await next-generation extremely large telescopes with sufficient sensitivity to detect IMF-sensitive features in high redshift spectra. Metallicity, the abundance of elements heavier than helium, affects stellar spectra and evolutionary tracks significantly. Low metallicity stars have hotter surfaces, higher luminosities, and different spectral features compared to solar metallicity counterparts. Stellar population synthesis models account for these effects by computing evolution at various metallicities. But most model grids sample metallicities down to only about 1/50th solar, while the earliest galaxies might have metallicities below 1/100th solar or even lower. Extrapolating models to such low metallicities introduces uncertainties because the stellar physics changes mass, loss rates decline, convection zones shift, and fusion products alter in ways not fully captured by stellar evolution codes calibrated on higher metallicity stars. Binary star interactions add complexity, often neglected in standard synthesis models. Roughly half of massive stars reside in binary or multiple systems where gravitational interactions significantly alter their evolution. Mass transfer between companions can extend lifetimes, trigger earlier supernovae, or produce exotic outcomes like blue supergiants that wouldn't exist in isolation. Advanced synthesis codes like BPAS include binary evolution, producing spectra differing from single-star models, particularly in ultraviolet wavelengths and emission line strengths. If binary fractions were higher in the early universe, perhaps due to the fragmentation properties of low metallicity gas, neglecting binary evolution could systematically bias mass estimates. However, computational expense limits the parameter space these models explore, and uncertainties in binary interaction physics rival those in single-star evolution. Stellar rotation and magnetic fields also influence evolution, particularly for massive stars. Rapidly rotating stars mix their interiors more efficiently, dredging up fusion products and extending main sequence lifetimes. Strong magnetic fields affect mass loss and surface abundances. Both effects alter spectra and luminosities in ways standard synthesis models typically ignore or treat simplistically. In low metallicity environments, where mass loss through stellar winds is reduced, rotation might dominate internal mixing, producing stellar populations with enhanced helium and nitrogen surface abundances. Some observed high redshift galaxy spectra show unusually strong nitrogen emission lines, potentially indicating rotationally mixed stellar populations, though alternative explanations involving intensive nitrogen production in intermediate mass stars also exist. Nebula emission contributes significantly to early galaxy spectra, but is treated with varying sophistication in different models. When massive stars ionize surrounding gas, that gas emits strongly in lines like H-alpha, H-beta, and doubly ionized oxygen, potentially dominating total galaxy light in certain wavelength ranges. Standard stellar population synthesis produces only stellar spectra, requiring separate photoionization modeling to predict nebula emission. The nebula contribution depends on the ionizing photon production rate, gas density, metallicity, and geometry, all uncertain in early galaxies. Different research groups treat nebula emission differently. Some include it fully, using photoionization codes like cloudy. Others apply simple corrections, and some neglect it. These choices alter derived stellar masses, particularly for young, intensely star-forming systems where nebula emission is strongest. Dust modeling introduces additional uncertainties already discussed, but its interaction with stellar population synthesis deserves emphasis. Dust doesn't just attenuate light uniformly, it scatters light directionally and absorbs preferentially at short wavelengths, with efficiencies depending on grain properties. Different dust attenuation curves empirical descriptions of how extinction varies with wavelength are used in different studies, derived from observations of local starbursts, the Milky Way, or the Small Magellanic Cloud. If early universe dust has different grain-size distributions or compositions, none of these local templates apply correctly. Furthermore, dust's spatial distribution relative to stars matters. Dust mixed uniformly with stars attenuates differently than a foreground dust screen. Most models assume simple geometries that may not represent complex early galaxy structures. Given these myriad uncertainties, the most robust approach involves comparing multiple independent techniques and examining consistency. For JADESGSZ 130, researchers applied various synthesis codes with different IMF assumptions, metallicity ranges, dust curves, and nebula treatments. The resulting stellar mass estimates spanned nearly an order of magnitude from 30 million to 300 million solar masses, with the best estimate value around 100 million solar masses when adopting standard assumptions. This large range illustrates the challenge. Without perfect knowledge of stellar populations, IMF, binaries, dust, and geometry, stellar masses derived from photometry and spectroscopy carry substantial systematic uncertainties that can easily accommodate factors of 2 to 3 even with high-quality data. Alternative explanations: population 3 stars and top-heavy IMFs. Population 3 stars, the first generation born from primordial gas containing virtually no heavy elements, represent one potential explanation for unexpectedly bright early galaxies. These hypothetical stars would have formed under radically different conditions from all stars observed today. Without metals to facilitate cooling, primordial gas clouds had to reach higher temperatures before fragmenting, likely favouring formation of very massive stars, perhaps 100 to 300 solar masses, far larger than typical stellar masses today. Such massive stars would be extraordinarily luminous, with luminosities reaching millions of times the Sun's, and extremely hot, with surface temperatures exceeding 100,000 Kelvin. A single population 3 star could outshine an entire modern dwarf galaxy. If a significant fraction of early galaxies' light came from ongoing population 3 star formation, their apparent brightness could exceed expectations without requiring correspondingly large stellar masses. Massive stars live only a few million years before exploding as supernovae, so sustained population 3 formation could produce immense luminosity with relatively little accumulated stellar mass. The stellar mass consists primarily of long-lived low-mass stars and remnants from dead massive stars, while the luminosity is dominated by currently burning massive stars. If the ratio of massive to low-mass stars is higher in population to 3 populations than in modern populations a top-heavy IMF, then luminosity per unit stellar mass increases dramatically, potentially explaining bright, high redshift galaxies without invoking implausibly large masses. Theoretical models of population 3 star formation support the idea that the IMF was top-heavy, though the degree remains uncertain. Simulations of collapsing primordial gas clouds show that fragmentation is suppressed at low metallicity, producing fewer, more massive fragments compared to metal-enriched clouds. However, these simulations face resolution limitations. They cannot follow the collapse down to stellar scales and must make assumptions about physics at unresolved scales. Different numerical methods and subgrid prescriptions produce results ranging from a characteristic population 3 stellar mass of 10 solar masses to over 500 solar masses, with some models producing predominantly massive stars and others generating broader mass distributions including lower mass stars. Observational constraints on population 3 stars are limited because none have been directly detected. If population 3 stars existed, they should have exploded as supernovae after a few million years, enriching surrounding gas with the first metals. Subsequent star formation would incorporate these metals, transitioning to population 2 stars with measurably higher metallicities. The least metal-poor stars, observed in the Milky Way's halo, have metallicities around 1/100 zeroth solar, suggesting they formed from gas enriched by just one or a few population 3 supernovae. These ancient stars' abundance patterns constrain population 3 properties. Their high carbon to iron ratios suggest population 3 progenitors were massive but not ultramassive. probably in the range 20 to 100 solar masses rather than several hundred. Searching for population 3 signatures in high redshift galaxies faces challenges. Pure population 3 populations would produce distinctive spectra. Extremely hot temperatures produce copious ionizing radiation and strong helium emission lines with negligible metal lines. However, after just a few million years, supernovae enrich the gas, and subsequent star formation produces metal lines that dominate spectra. Detecting a galaxy in the brief, pure population 3 phase requires catching it during its first few million years of star formation, a tiny window in cosmic time. Most high redshift galaxies observed show metal emission lines, indicating they have already transitioned beyond pure population 3. Claims of population 3 detections based on unusually strong helium emission have been made but remain controversial, with alternative explanations involving very hot O-type stars in low metallicity populations. A more realistic scenario involves ongoing but subdominant population 3 formation mixed with population 2 star formation in early galaxies. Small pockets of primordial gas, perhaps shielded from metal enrichment in remote regions of the galaxy, or accreting pristinely from the intergalactic medium, could continue forming population 3 stars even as most of the galaxy evolves. Chemically, these pockets would boost total luminosity without dramatically altering the spectrum, because population 2 stars outnumber them. Modelling this mixed scenario is complex, requiring assumptions about what fraction of star formation occurs in pristine versus enriched gas, and how this fraction evolves with time. Different choices can alter inferred stellar masses by factors of 2, but probably cannot reduce masses enough to fully resolve the tension with theoretical predictions, which exceed observations by factors of 5 to 10 inches extreme cases. Top-heavy IMFs, not limited to pure population 3 populations, provide a more general possibility. Even in metal-enriched gas, if environmental conditions favour massive stars, perhaps due to high gas temperatures, strong radiation fields, or turbulent pressures in intensely star-forming regions, the IMF could be systematically shifted toward higher masses compared to local galaxies. Observational evidence for top-heavy IMFs in extreme local starbursts exists. Ultraluminous infrared galaxies show emission line ratios and chemical abundances, potentially indicating enhanced massive star formation. If early galaxies universally resembled these extreme systems, a moderately top-heavy IMF, not as extreme as pure population 3, but shifted relative to salpeter, could reduce inferred stellar masses by factors of 2 to 3 while still matching observed luminosities. Testing the IMF in early galaxies requires spectral diagnostics sensitive to the massive to low mass star ratio. Emission line ratios involving hydrogen, helium, oxygen, and nitrogen provide clues. Different combinations of stellar masses and metallicities produce characteristic patterns in these ratios. For example, high helium to hydrogen ratios indicate hot, massive stars, while nitrogen to oxygen ratios trace intermediate mass star contributions. Some high redshift galaxy spectra show elevated nitrogen and helium, potentially consistent with top-heavy IMFs, but theoretical models of chemical evolution can produce similar patterns through rapid cycling of massive stars in starbursts, even with standard IMFs. Distinguishing these scenarios demands high signal-to-noise spectroscopy resolving multiple weak emission lines, observations that push current capabilities but will become routine with future instruments. The Hubble tension and its possible connection. The Hubble tension, a persistent discrepancy in measurements of the universe's expansion rate, has emerged as another potential challenge to standard cosmology. The Hubble constant describes how fast the universe expands, typically expressed in kilometers per second per megaparsec. Two independent measurement approaches yield inconsistent values. Early universe observations, particularly the cosmic microwave background mapped by Planck, give H0 approximately equal to 67 kilometers per second per megaparsec, while late universe measurements using distance ladders anchored by Cepheid variables and supernovae give H0 approximately equal to 73 kilometers per second per megaparsec. This 9% difference exceeds measurement uncertainties, suggesting either systematic errors in one or both methods or new physics beyond the standard Lambda-CDM model. The connection to early galaxy observations isn't immediately obvious, but becomes apparent when considering how the Hubble constant affects structure formation. A higher Hubble constant means the universe expanded faster in the past, so structures at any given redshift would have formed more recently. There would be less time between the Big Bang and that redshift. This might seem to worsen the early galaxy problem. If less time elapsed before redshift 13, galaxies would have even less time to assemble their observed stellar masses. However, the situation is more nuanced because the Hubble constant also affects the universe's matter, density, age, and the amplitude of initial density fluctuations, all of which influence structure formation rates. Some proposed solutions to the Hubble tension involve early dark energy, a component of dark energy that was significant in the early universe rather than only dominating recently. Standard Lambda-CDM assumes dark energy's density remains constant while matter density decreases as the universe expands, so dark energy's influence grows over time. Early dark energy models propose that dark energy had higher density in the past, affecting the expansion rate differently at early versus late times. This could potentially reconcile CMB-based and distance ladder-based Hubble constant measurements by introducing additional freedom in the expansion history. Interestingly, early dark energy models can affect structure formation in ways that might help explain unexpectedly abundant high redshift galaxies. If dark energy was more significant at high redshift than Lambda-CDM assumes, it would have accelerated expansion more at those times, but it could also modify the growth rate of density perturbations in compensating ways. Depending on specific model parameters, early dark energy can either suppress or enhance structure formation at particular scales and epochs. Some parameter choices boost the amplitude of small-scale fluctuations relevant for galaxy mass halos, while remaining consistent with CMB observations that primarily constrain larger scales. This could increase the number density of early galaxies, potentially bringing theory closer to JWST observations. However, early dark energy faces its own challenges. Detailed analyses show that while it can reduce the Hubble tension, it doesn't eliminate it entirely, and it introduces new tensions with other observations, including baryon, acoustic oscillations, and measurements of galaxy clustering at intermediate redshifts. Furthermore, most early dark energy models that boost high redshift structure formation do so modestly, perhaps factors of 1.5 to 2, insufficient to explain the most extreme cases observed by JWST, where discrepancies reach factors of 5 to 10. The approach remains an active research area, with ongoing debates about whether fine-tuned parameter choices can simultaneously resolve multiple tensions, or whether the required fine-tuning suggests the models are contrived. Another possible connection involves the matter-power spectrum, the distribution of density fluctuations across different spatial scales. The CMB measurements from Planck constrain this spectrum's amplitude and shape at the time of recombination, 380,000 years after the Big Bang, on relatively large scales. Galaxy surveys constrain it at later times and smaller scales. A known tension exists in the parameter S8, which characterizes the spectrum's amplitude. CMB-based values are slightly higher than values inferred from weak gravitational lensing surveys and galaxy clustering at low redshift. This tension suggests either that structure growth has been slower than predicted, or that systematic errors affect one or both measurement approaches. If S8 is truly lower than Planck predicts, structure formation would proceed more slowly throughout cosmic history, potentially worsening the early galaxy problem. However, if instead S8 is scale-dependent, higher at small scales relevant for galaxies, lower at large scales relevant for clusters, it could boost early galaxy formation while maintaining consistency with low redshift observations. Some modified gravity theories, or dark sector interactions, predict scale-dependent structure growth, though such models are highly constrained by multiple independent observations. The interplay between these various tensions, Hubble constant S8, and early galaxy abundances, motivates unified explanations involving new physics. But no compelling single solution has yet emerged that simultaneously resolves all discrepancies while remaining consistent with the full range of cosmological data. What JWST continues to reveal. Since its launch in December 2021 and first light observations in mid-2022, JWST has continued producing discoveries that challenge and refine our understanding of early galaxy formation. The telescope's capabilities sensitivity at infrared wavelengths from 0.6 to 28 microns, spatial resolution approaching Hubble's despite longer wavelengths, and spectroscopic instruments capable of analyzing faint, distant galaxies make it uniquely suited for studying the high redshift universe. Each new deep field observation and spectroscopic campaign adds galaxies to the census at redshifts 10 and beyond, gradually building statistical samples that can test whether the earliest discoveries represent rare outliers or typical populations. By late 2024, JWST had spectroscopically confirmed dozens of galaxies at redshifts above 10, with several exceeding redshift 13 and even candidates at redshift 15 to 16, pending confirmation. This growing sample reveals diversity. Some galaxies are compact and faint, matching theoretical expectations, while others remain unexpectedly bright and extended. The distribution of properties, stellar masses, sizes, star formation rates, shows that while typical early galaxies perhaps align with predictions, the high mass tail of the distribution is more populated than models suggested. In statistical terms, the number of galaxies exceeding 100 million solar masses at redshift 12 to 14 appears elevated by factors of 3 to 5 compared to simulations, a discrepancy that persists across multiple independent surveys and analysis methods. Spectroscopic observations have revealed chemical abundances in the earliest galaxies, showing surprisingly high metallicities in some systems. Oxygen, the most easily measured metal, shows abundances reaching 10 to 20% of solar values in galaxies at redshift 10 to 13. This rapid enrichment implies that multiple generations of stars had already formed, lived, and exploded by these early times, distributing their processed elements throughout the interstellar medium. The nitrogen to oxygen ratios measured in some galaxies are also surprisingly high, potentially indicating contributions from intermediate mass stars that require tens of millions of years to evolve, difficult to reconcile with the limited time available. Alternative explanations involving rotationally induced mixing in massive stars or intensive nitrogen production in very massive stars remain under investigation. JWST has also detected supermassive black holes in remarkably early galaxies, Broad emission lines characteristic of gas swirling around black holes at high velocities have been identified in galaxies at redshifts 8 to 11, indicating black hole masses reaching millions of solar masses. The presence of such massive black holes so early poses its own puzzle. Black holes grow by accreting gas and merging with other black holes, processes that take time. Standard accretion theory predicts that even if black holes started from massive seeds, perhaps 100 solar masses from population 3 supernovae, or 10,000 solar masses from direct collapse of gas clouds, couldn't reach millions of solar masses by redshift 10 without accreting continuously at maximal rates. The Eddington limit constrains how fast black holes can grow. Radiation pressure from accreting material opposes infall, setting a maximum accretion rate. Super Eddington accretion is possible under specific conditions, but carries physical challenges. The discovery of early supermassive black holes suggests either that black hole seeds were heavier than expected, that Super Eddington accretion was common, or that our understanding of black hole growth needs revision. The morphologies of high redshift galaxies observed by JWST show interesting patterns. Many appear clumpy and irregular, with multiple bright knots of star formation rather than smooth light distributions. This clumpiness matches expectations for young, actively assembling galaxies where gas infall and star formation occur episodically in dense pockets. However, a subset shows surprising regularity, disk-like or even spiral-like structures at redshifts 8 to 10, implying that at least some galaxies had settled into rotationally supported disks remarkably early. In standard hierarchical assembly, galaxies spend hundreds of millions of years undergoing chaotic mergers before settling into stable disks. Finding disk galaxies at redshift 10 corresponding to 480 million years after the Big Bang suggests either that these particular systems formed unusually smoothly, avoiding major mergers, or that disk formation can occur faster than models predict. JWST's spectroscopic surveys have also constrained reionization's progress by measuring the neutral hydrogen fraction at different redshifts through the strength of Lyman alpha absorption. Galaxies at redshift 8 show strong Lyman alpha emission, indicating the universe was largely ionized by that time. At redshift 10, some galaxies show Lyman alpha, while others don't, suggesting ionization was patchy, completed in some regions, but ongoing in others. Above redshift 12, Lyman alpha detection becomes rarer, though a few detections exist, implying that reionization was perhaps half complete by redshift 13. This timeline is slightly earlier than some previous estimates, but remains consistent with the overall picture that reionization occurred between 300 million and 1 billion years after the Big Bang. Ongoing and planned JWST programs will continue addressing these questions. The JADE survey is executing additional deep spectroscopic observations targeting fainter galaxies, pushing toward lower masses and more typical systems. The CEERS and Cosmos Web surveys are covering larger areas to find rare, extremely luminous galaxies and assess their true number densities. Targeted observations of individual galaxies with longer integration times are obtaining high signal-to-noise spectra resolving weak emission lines, enabling detailed chemical abundance measurements and constraints on stellar populations and IMFs. Coordinated observations with ground-based telescopes like ALMA, measuring dust and gas properties, complement JWST's stellar and ionized gas measurements, building comprehensive pictures of early galaxies' physical conditions. Implications for our understanding of galaxy formation. The discoveries from JWST force astronomers to reconsider fundamental assumptions about how galaxies form and evolve. For decades, the hierarchical assembly picture small structures merging into progressively larger ones over cosmic time provided a successful framework explaining galaxy properties across a wide range of masses and redshifts. This framework, rooted in Lambda-CDM cosmology and tested through extensive simulations, predicted that massive galaxies should be rare or absent at very high redshift because insufficient time had passed for hierarchical build-up. The presence of numerous massive, mature galaxies at redshift 10 and beyond challenges this picture, though it doesn't necessarily overturn it completely. Several possibilities exist for reconciling observations with theory. First, the discrepancy might be smaller than it appears if systematic uncertainties in mass estimates are larger than currently assessed. Revisiting assumptions about stellar populations, IMFs, dust properties, and emission line contributions could systematically reduce inferred stellar masses by factors of 2 to 3. Combined with possible upward revisions to theoretical predictions, if certain feedback mechanisms were weaker than assumed, or if galaxy formation efficiency was higher in specific environments, the gap might narrow to tolerable levels. This conservative approach preserves the basic Lambda-CDM framework while acknowledging that galaxy formation physics contains complexities not fully captured in current simulations. Second, the cosmological parameters themselves might need adjustment. While Lambda-CDM is well constrained by CMB and large-scale structure observations, subtle modifications within observational uncertainties could affect high redshift structure formation. For example, slightly higher values of the matter density or scalar spectral index parameters describing the amplitude and shape of primordial fluctuations could boost early structure formation. Alternatively, primordial non-Gaussianity deviations from purely Gaussian random initial conditions could enhance the abundance of high-mass halos at early times. These modifications would need to remain consistent with all other cosmological observations to a challenging requirement, but exploring this parameter space is worthwhile. Third, new physics beyond the standard model might be required. This is the most radical option and thus subject to the highest skepticism, but persistent tensions could eventually motivate it. Possibilities include additional dark sector particles or interactions affecting structure formation, exotic dark energy behavior at high redshift, or modifications to gravity altering how structures collapse and grow. Each of these would represent a major shift in fundamental physics and would require extensive testing against diverse observations. Most physicists regard such explanations as premature standard physics hasn't been exhausted yet, but they remain logical possibilities if other solutions fail. Regardless of which explanation proves correct, JWST observations have already refined our understanding of specific processes. The rapid chemical enrichment observed indicates that stars formed efficiently in the early universe, and that supernovae distributed their products throughout galaxies quickly, perhaps more efficiently than in local systems. The presence of dust so early confirms that grain formation in supernova ejecta is efficient and rapid, occurring within millions of years of stellar birth. The detection of black holes growing vigorously at high redshift shows that whatever seeding mechanism initiated black hole formation, whether population 3 remnants, direct collapse, or something else, operated effectively and early. The morphological diversity seen in high redshift galaxies suggests multiple formation pathways. Some galaxies may have assembled smoothly through steady gas accretion along filaments, forming disk-like structures directly without major mergers. Others clearly show signs of merger activity, with multiple clumps and irregular morphologies. This diversity mirrors what's seen at lower redshifts and suggests that galaxy formation isn't a monolithic process, but depends on local environmental conditions, gas supply rates, merger history, and other factors varying from galaxy to galaxy. The implications extend beyond galaxy formation to broader cosmology. If early galaxies contributed more ionizing photons than expected, they would have accelerated reionization, potentially explaining why the universe became fully ionized by redshift 6, rather than lingering partially neutral until later times. The exact timing and topology of reionization, whether it proceeded inside out from dense regions or in a more complex pattern, depend on the abundance and properties of early galaxies, making JWST observations directly relevant to understanding this critical phase transition, the future of early universe observations. JWST's discoveries represent just the beginning of a new era in high redshift astronomy. The telescope will continue operating for potentially 20 years, conducting increasingly sophisticated observations as astronomers refine their strategies based on early results. Future JWST programs will focus on building larger statistical samples, obtaining deeper spectroscopy for detailed physical characterization, and coordinating with other facilities to probe complementary wavelength ranges and physical properties. These efforts will gradually clarify whether the earliest discoveries represent the true galaxy population, or whether selection effects and systematic uncertainties have biased initial results. Complementary observations from ground-based telescopes provide crucial context. ALMA observes at millimeter and sub-millimeter wavelengths, detecting cold dust and molecular gas that trace star formation and provide independent mass estimates. While observing time on ALMA is precious and limited, targeted programs focusing on the brightest JWST-detected galaxies are obtaining dust, continuum, and emission line measurements that constrain gas masses, dust temperatures, and kinematics. These data test whether high redshift galaxies contain sufficient gas to sustain their inferred star formation rates, and whether their dynamical masses match stellar mass estimates from JWST. Next-generation ground-based telescopes will greatly expand capabilities. The extremely large telescope, ELT, in Chile, with a 39-meter primary mirror, will achieve spatial resolution and sensitivity far exceeding current facilities. Its infrared spectrographs will obtain detailed spectroscopy of high redshift galaxies, resolving velocity structures, measuring chemical abundance gradients, and detecting faint emission lines invisible to JWST. The Giant Magellan Telescope, GMT, and 30-meter telescope, TMT, with 25-meter and 30-meter mirrors, respectively, will provide similar capabilities. These facilities, expected to begin operations in the late 2020s and early 2030s, will scrutinize JWST discoveries in unprecedented detail, testing stellar population models, constraining IMFs, and measuring spatially resolved properties that reveal internal structure. Space-based missions beyond JWST are also planned. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, carries a wide-field imager covering larger areas of sky than JWST, though with less sensitivity per pointing. Roman surveys will find rare, extremely bright, high redshift galaxies if they exist, providing statistics on the bright end of the luminosity function. ESA's Euclid mission, launched in 2023, conducts wide-area infrared imaging that complements JWST's deep pencil beam surveys, enabling studies of how galaxy properties vary across cosmic environments at all redshifts. Far future concepts include space telescopes, even larger than JWST designs, with 10 to 15 meter mirrors that could image individual star clusters in high redshift galaxies and obtain spectroscopy, currently impossible. Advances in theoretical modelling will accompany observational progress. Next-generation cosmological simulations are incorporating improved physics, more sophisticated star formation, and feedback prescriptions calibrated against JWST observations, explicit treatment of binary stellar populations, improved dust and metal enrichment models, and higher resolution, allowing smaller galaxies to be simulated realistically. Machine learning techniques are being applied to extract maximum information from simulations and observations. Neural networks trained on simulated galaxy properties can predict masses and ages from observed photometry more accurately than traditional template fitting, while generative models can create synthetic galaxy populations matching observed statistics to constrain underlying physical parameters. The combination of JWST observations, complementary facilities, and advanced simulations will eventually answer whether the early bright galaxies represent a crisis for Lambda-CDM or a challenge requiring refined galaxy formation physics. The distinction is crucial. The former would necessitate revising fundamental cosmology, while the latter would advance astrophysical understanding within the existing framework. Current evidence, though surprising, hasn't yet crossed the threshold requiring abandonment of standard cosmology, but the next few years of observations will be decisive. If the tension persists and grows, as systematics are eliminated and samples expand, the case for new physics will strengthen. If instead, refined analyses bring observations and theory into agreement, JWST will have succeeded in its mission to test and validate our cosmic origin story. Gravitational lensing, magnifying the distant universe. When astronomers want to see the faintest, most distant galaxies in the universe, they sometimes rely on nature's most powerful telescope, gravity itself. Gravitational lensing, the bending of light by massive objects, predicted by Einstein's general relativity, can magnify background galaxies by factors of 10, 100, or even more, bringing otherwise invisible objects into view. This cosmic magnification has become an essential tool for studying the high redshift universe, allowing JWST to peer even deeper than its remarkable sensitivity alone would permit. Some of the brightest early galaxies detected appear so luminous partly because massive foreground galaxy clusters act as natural lenses, stretching and brightening their images. Einstein's general relativity predicts that mass warps the fabric of space-time, causing light rays to follow curved paths when passing near massive objects. For most astronomical situations, this bending is tiny. The sun deflects starlight passing near its limb by only 1.75 arcseconds, barely measurable. But galaxy clusters containing the mass of thousands of trillions of suns create much stronger distortions. Light from distant background galaxies passes through the warped space-time around these clusters, bending toward us. The cluster acts as a lens, focusing light that would otherwise miss Earth, effectively increasing the background galaxy's apparent brightness and size. The magnification depends on the precise alignment between observer, lens, and source. Perfect alignment produces Einstein rings, circular or nearly circular arcs of light surrounding the lensing mass. Slight misalignments create giant arcs, stretched, distorted images of background galaxies that can span tens of arcseconds across the sky. Multiple images can appear when light takes different paths around the lens, creating duplicates of the same galaxy at different positions. The magnification factor varies across the lensed image. Some regions might be magnified tenfold, others 30-fold, with the exact pattern determined by the lens's mass distribution. For high redshift galaxy studies, gravitational lensing provides crucial advantages. First, magnification boosts apparent brightness, making faint galaxies detectable with shorter exposure times. A galaxy magnified 20-fold appears 20 times brighter, reducing required integration time by a factor of 400, transforming a 100-hour observation into a 15-minute one. Second, magnification increases apparent size, allowing spatial structures to be resolved. A galaxy 1,000 light-years across at redshift 13 normally appears smaller than JWST's resolution limit. But with 20-fold magnification, structures as small as 50 light-years become resolvable. Third, lensing provides independent mass measurements. Modelling the lens precisely enough to reproduce observed arc positions and shapes requires accurate mass distributions, and comparing this dynamical mass to stellar mass estimates tests whether dark matter halos have expected properties. Several famous galaxy clusters serve as gravitational telescopes for high redshift surveys. Abell, 2744, nicknamed Pandora's cluster, has been extensively studied by both Hubble and JWST. Its complex mass distribution produces numerous giant arcs and multiple images, magnifying background galaxies at redshifts 6 to 10 by factors of 5 to 50. Max J416, another powerful lens, creates spectacular arc systems that have revealed some of the highest redshift galaxies known. The Hubble Frontier Fields program, which preceded JWST, observed 6 such clusters in unprecedented detail, discovering hundreds of lensed high redshift galaxies that provided the first hints of abundant early structure formation. JWST's observations of lensing clusters have uncovered extremely faint galaxies magnified into visibility. Some of these systems, intrinsically containing only a few million solar masses of stars, appear bright enough for detailed spectroscopy thanks to magnification factors exceeding 50. These observations probe the low-mass end of the galaxy population at high redshift dwarf galaxies too faint to detect in blank field surveys. Theoretical models predict these dwarfs should be numerous and collectively important for reionization, but observational confirmation requires gravitational lensing to make them detectable. JWST data are beginning to provide this confirmation, showing that low-mass galaxies are indeed abundant at redshift 10 and beyond. Lensing magnification isn't uniform across a galaxy's extent, creating differential magnification that can distort physical property measurements. If one region of a galaxy is magnified 30-fold, while another is magnified 10-fold, the highly magnified region dominates the observed light, potentially biasing measurements of size, brightness distribution, and internal structure. Careful lens modeling accounts for these effects, reconstructing the galaxy's intrinsic properties by inverting the lensing distortion. This process requires detailed mass models of the lensing cluster, typically constructed by fitting multiple arc systems simultaneously. Uncertainties in lens models translate to uncertainties in source properties, but modern techniques using hundreds of constraints from multiple images can determine magnification factors to within 10 to 20%. Strongly lensed galaxies also enable unique science beyond simple detection. Time delays between multiple images of variable sources, if a star brightens or a supernova explodes, provide independent constraints on the lens mass distribution and even the Hubble constant, since time delays depend on cosmic geometry. For extended sources like galaxies, differential time delays across the source can be measured through careful monitoring, probing the source's structure. Microlensing by individual stars in the lensing cluster can further magnify small regions, potentially resolving individual star clusters, or even supergiant stars in high redshift galaxies, observations impossible without this cosmic microscope. Despite its power, gravitational lensing introduces challenges. Lens modeling requires assumptions about the mass distribution, whether dark matter follows smooth profiles or contains substructure, whether the cluster has undergone recent mergers, creating disturbed mass distributions. Different modeling techniques and assumptions can yield magnification estimates differing by factors of 2 or more, particularly near critical curves where magnification diverges toward infinity. These systematic uncertainties must be carefully propagated through to final physical property measurements. Additionally, lensing clusters occupy special, overdense regions of the universe, so galaxies found behind them might not be representative of the average population. Studies must account for this environmental bias when interpreting number densities and comparing with theoretical predictions for the general field population. Some early JWST discoveries, initially thought to be unlensed, high redshift galaxies, were later identified as lensed, lower redshift systems. Careful examination revealed faint lensing clusters in the foreground, or subtle arc-like morphologies indicative of lensing. These cases highlight the importance of thorough analysis before claiming extraordinary properties. Conversely, some genuinely high redshift systems might be weakly lensed by foreground structures, receiving modest magnification factors of 1.5 to 3 that wouldn't produce obvious distortions. Accounting for this statistical lensing is important for accurate number density estimates. Future observations will continue exploiting gravitational lensing. JWST programs are targeting additional lensing clusters, building comprehensive samples of lensed high redshift galaxies spanning wide luminosity and mass ranges. Coordinated observations with ALMA measure lensed galaxies' dust and gas content, while ground-based telescopes obtain optical spectroscopy and monitor for variability. The upcoming extremely large telescopes will image lensed galaxies with extraordinary resolution, potentially resolving individual star-forming regions and measuring velocity fields tracing internal dynamics. As lens modeling improves and samples grow, gravitational lensing will remain an indispensable tool for studying the universe's first galaxies, providing magnified views of cosmic dawn that would otherwise remain forever hidden in the faint background glow, the physics of redshift space distortions. Understanding the precise distances and velocities of high redshift galaxies requires grappling with redshift space distortions, systematic effects that modify how galaxies appear distributed in maps constructed from redshift. Measurements. These distortions arise because redshift doesn't measure distance directly. It measures the combined effect of cosmic expansion and an object's peculiar velocity, its motion through space, relative to the overall expansion flow. In the local universe, peculiar velocities cause minor corrections to distance estimates. But in the early universe, where galaxies were still assembling and gravitational dynamics were vigorous, peculiar velocities and their effects on apparent positions became significant, affecting interpretations of galaxy clustering, number densities, and large-scale structure. Redshift has two components, cosmological and Doppler. Cosmological redshift arises from the expansion of space itself as the universe expands. Photon wavelengths stretch proportionally. This component directly traces distance. Galaxies farther away have higher cosmological redshifts because space has expanded more during their light's journey. Doppler redshift arises from an object's motion toward or away from us through space. If a galaxy moves toward us at velocity v, its light is blue shifted by approximately v divided by c, where c is the speed of light. If moving away, it's redshifted by the same amount. Observed redshift combines both effects, but only the cosmological component relates directly to distance. In the early universe, galaxies moved vigorously under gravity's influence. Gas accreted along dark matter filaments. Galaxies fell toward overdense regions that would become clusters. and merger events imparted large velocity kicks. These peculiar velocities reached hundreds or even thousands of kilometers per second, modest compared to the speed of light, but significant compared to redshift uncertainties. A galaxy at redshift 10 moving toward us at 1,000 kilometers per second experiences a Doppler blue shift of roughly z equals 0.003, while, if moving away, it experiences a redshift of the same amount. Since redshift intervals from z equals 10 to z equals 10.003 correspond to distance differences of several million light-years, peculiar velocities can place galaxies tens of millions of light-years from their true positions in redshift-based maps. The effect systematically distorts apparent clustering patterns. On large scales, galaxies falling into overdense regions, like protoclusters, experience velocities directed toward the overdensity's center. Along the line of sight, galaxies on the near side are falling toward us, while those on the far side are falling away, compressing the structure's apparent depth in redshift space, an effect called the Kaiser effect, or squashing. Perpendicular to the line of sight, no systematic effect occurs because transverse velocities don't affect redshift. This creates a characteristic anisotropy. Clusters and filaments appear compressed along the line of sight, elongated perpendicular to it, producing pancake shapes in redshift maps, even if intrinsically spherical. On small scales within galaxies or groups, virial motions, random velocities of objects orbiting within the gravitational potential produce an opposite effect called fingers of God. Galaxies within a cluster orbit at high speeds in random directions. Those orbiting toward us appear blue-shifted, placed at smaller distances. Those orbiting away appear redshifted, placed at larger distances. This spreads the cluster out along the line of sight, creating elongated fingers pointing toward the observer. The elongation magnitude depends on velocity dispersion, the spread in orbital speeds, which traces the cluster's mass. Massive clusters with deeper gravitational potentials have higher velocity dispersions and longer fingers. For high redshift observations, accounting for these distortions becomes crucial when estimating galaxy number densities and clustering properties. If peculiar velocities systematically shift galaxies from their true redshifts, volume calculations will be incorrect. A structure at z equals 10.5, appearing to span delta z equals 0.1 due to virial motions, occupies less true volume than assumed if peculiar velocities are ignored, artificially inflating number density estimates. Conversely, if galaxies are clustered in filamentary structures compressed in redshift space, the apparent clustering strength will differ from the intrinsic clustering, affecting comparisons with simulations that predict real space clustering. Measuring peculiar velocities directly is difficult because it requires knowing both the observed redshift and the true cosmological redshift, which itself depends on distance, creating circular logic. Several methods break this degeneracy. For nearby galaxies, independent distance measurements using standard candles like Cepheids or supernovae provide true distances, and subtracting the expected cosmological redshift for that distance reveals the peculiar velocity. At high redshift, this isn't feasible because standard candles are too faint. Instead, statistical approaches examine clustering patterns anisotropy, comparing clustering strength parallel versus perpendicular to the line of sight reveals the redshift space distortion signature, from which average peculiar velocities can be inferred. The magnitude of redshift space distortions depends on the growth rate of cosmic structure, parametrized by f equals omega, m to the power of 0.55, where omega m is the matter density parameter. This dependence makes redshift space distortions a probe of cosmological parameters, and even tests of general relativity. If gravity behaves differently from GR's predictions, structure growth rates differ, altering redshift space distortion patterns. Measurements at various redshifts trace how the growth rate evolves with time, constraining dark energy properties and testing whether cosmic acceleration arises from dark energy or modified gravity. At redshift 10 and beyond, current observations lack sufficient sample sizes for statistical redshift space distortion measurements. JWST surveys find dozens to hundreds of galaxies at these redshifts, insufficient for robust clustering analysis requiring thousands of objects. However, as samples grow, such analyses will become possible, testing whether structure growth in the early universe proceeded as Lambda-CDM predicts. Any deviations would signal new physics, perhaps modifications to gravity relevant in strong field regimes or exotic dark matter properties affecting small-scale clustering. Another subtlety involves relativistic effects. At high redshift, galaxies move at velocities approaching light speed relative to the CMB rest frame. The Milky Way moves at roughly 600 km per second relative to the CMB, and this motion adds to observed redshifts depending on viewing direction. For distant galaxies, we must account for the Milky Way's motion, Earth's motion around the Sun, and the Sun's motion through the galaxy. These corrections are small, typically delta Z, approximately 0.002, but not negligible compared to redshift uncertainties for faint galaxies. Additionally, gravitational redshift from photons climbing out of galaxies' gravitational potentials creates systematic shifts. For dwarf galaxies, this is tiny, but for galaxies embedded in massive dark matter halos, the effect reaches delta Z, approximately 0.001, subtly biasing redshift measurements. Understanding these effects ensures accurate interpretation of high redshift observations. When estimating whether observed galaxy abundances match theoretical predictions, volumes must be calculated correctly, accounting for how peculiar velocities affect redshift distributions. When comparing observed clustering with simulations, transforming simulation outputs into redshift space using the same distortions affecting real data enables fair comparisons. As JWST and future facilities build larger samples, sophisticated analyses incorporating redshift space distortions will extract maximum information, testing cosmological models and revealing the dynamical state of the early universe when galaxies were actively assembling. Primordial fluctuations, the seeds of cosmic structure. Every galaxy in the universe, including J, A, D, E, S, G, S, Z, 1, 3, 0, traces its origin to tiny density fluctuations imprinted during the first fraction of a second after the Big Bang. These primordial fluctuations, quantum variations in energy density, stretched to cosmic scales by cosmic inflation, provided the seeds from which all structure grew. Understanding their properties is fundamental to cosmology because they determine when and where dark matter halos collapse, which in turn determines when and where galaxies form. The fact that bright galaxies exist at redshift 13 carries profound implications for the amplitude and spectrum of primordial fluctuations, potentially revealing physics from the inflationary epoch 13.8 billion years earlier. Cosmic inflation, a brief period of exponential expansion occurring roughly 10 to the minus 35 seconds after the Big Bang, explains several cosmic mysteries. Why the universe is so spatially flat, why opposite sides of the sky have the same temperature despite being causally disconnected, and why large-scale structure appears statistically homogeneous. During inflation, quantum fluctuations in the inflaton field, the hypothetical field driving inflation, were stretched from subatomic to cosmic scales. When inflation ended and normal expansion resumed, these fluctuations became frozen in density variations. Some regions slightly denser than average, others slightly less dense. Gravity amplified these variations over billions of years, with denser regions attracting more matter and becoming galaxies and clusters, while less dense regions emptied into voids. The statistical properties of primordial fluctuations are characterized by the power spectrum, a mathematical description of how fluctuation amplitude varies with spatial scale. On the largest scales, corresponding to galaxy superclusters and beyond, fluctuations have amplitude approximately 10 to the minus 5 variations of 1 part in 100,000. On smaller scales relevant for individual galaxies, the amplitude depends on the spectrum's shape, parametrized by the spectral index n(s). A scale-invariant spectrum has n(s) equals 1, meaning fluctuations have equal amplitude at all scales. Observations from the cosmic microwave background, particularly from the Planck satellite, measure n(s) approximately equals 0.965, indicating slightly weaker fluctuations on small scales than large scales, a nearly scale-invariant spectrum as many inflation models predict. The precise value of n(s) affects when galaxies can form. If n(s) were significantly larger, say 1 or higher, small-scale fluctuations would be stronger, causing early collapse of galaxy mass halos and earlier galaxy formation. The observed value 0.965 means small-scale power is slightly suppressed, delaying galaxy formation modestly compared to a scale-invariant spectrum. This delay is why Lambda-CDM simulations predict relatively few massive galaxies at redshift 13, given the measured n, s, and other parameters. Structure growth proceeds at a specific rate, and reaching galaxy masses of 100 million solar masses by 325 million years after the Big Bang is statistically rare. Not impossible, but occurring in only the densest regions where fluctuations happen to be above average. If observations definitively confirm that massive galaxies are significantly more abundant than predicted, say 5 to 10 times more common, this would suggest either that n(s) is slightly larger than Planck measured, or that the power spectrum deviates from a simple power law. Primordial non-Gaussianity represents one such deviation. Instead of fluctuations following a Gaussian random distribution, they might show excess clustering on certain scales or asymmetries between overdense and underdense regions. Different inflationary models predict different non-Gaussianity patterns, so detecting primordial non-Gaussianity would constrain the physics of inflation itself, possibly ruling out entire classes of models. Current constraints on non-Gaussianity, parametrized by F, NL, come primarily from the CMB. Planck measurements find F, NL approximately equals 0 plus or minus 5, consistent with purely Gaussian fluctuations as simplest inflation models predict. However, substantial room exists for localized non-Gaussianity affecting only specific scales. If F, NL is non-zero on galaxy scales, it would enhance or suppress small-scale fluctuations relative to CMB-constrained large scales, potentially reconciling early galaxy abundances with cosmological parameters. Testing this requires comparing galaxy clustering at multiple redshifts with simulations incorporating non-Gaussianity, a program requiring large samples not yet available at Z greater than 10, but feasible in coming years. Another consideration involves the cutoff scale below which primordial fluctuations are suppressed. Standard inflation predicts fluctuations exist on all scales down to microscopic sizes, but variance involving phase transitions or alterations to the inflationary potential might suppress power below certain scales. If fluctuations were suppressed on scales corresponding to galaxy masses, early galaxy formation would be delayed. Conversely, enhanced fluctuations on those scales would accelerate it. Current observations probe scales from the CMB's 100 megaparsec features down to galaxy-scale measurements at lower redshift, finding smooth power spectra with no unexpected features. Extending measurements to higher redshift tests whether this continues to hold during the earliest epochs. The amplitude of fluctuations, parametrized by sigma 8 in the variance of density fluctuations, averaged over 8 megaparsec spheres, also critically affects early structure formation. Planck CMB measurements give sigma 8 approximately equals 0.81. But some lower redshift observations, particularly weak gravitational lensing surveys, suggest slightly lower values, around 0.76 to 0.78. This tension, related to the S8 parameter mentioned earlier, indicates either systematic uncertainties in measurements or new physics affecting how fluctuations grow. If sigma 8 is truly higher than lower redshift measurements suggest, structure would grow faster than those observations indicate, potentially explaining abundant high redshift galaxies. But this creates inconsistencies elsewhere, requiring careful analysis to determine whether a unified solution exists. The scale dependence of growth also matters. In standard Lambda-CDM with cold dark matter, all scales grow at the same rate, determined only by the cosmic expansion history. Alternative dark matter models, like warm dark matter, suppress growth on small scales because dark matter particles' residual velocities prevent collapse below certain masses. If dark matter were warmer than assumed, fewer low-mass halos would form early, reducing the number of proto-galaxies merging to form larger systems. This might seem to worsen the early galaxy problem, but depending on how star formation efficiency scales with halo mass, the effect could go either way. If star formation becomes more efficient in the fewer, slightly larger halos that do form, total galaxy abundances might increase despite fewer halos. Measuring primordial fluctuation properties from galaxy observations requires careful comparison with simulations. Cosmological simulations begin with initial conditions drawn from the measured power spectrum, evolve them forward using gravity and hydrodynamics, and predict galaxy properties at each redshift. By comparing predicted and observed galaxy abundances, clustering, and properties, astronomers constrain whether initial conditions were correctly characterized. Persistent discrepancies suggest either missing physics in simulations or incorrect initial conditions, potentially pointing to new insights about inflation and the universe's earliest moments. As JWST builds high redshift galaxy samples and new CMB observations refine primordial fluctuation measurements, the connection between the first, second, and the first galaxies will become ever clearer, possibly revealing profound truths about the universe's quantum origins